Hello?
Is your laptop? Yeah.
Yeah, it's connected.
Okay, cool.
Hey, Ethan, good to see you. Welcome.
A lot of people.
Yes, this will be fun.
Yeah, I met at the train station another high school kid.
No
It's
way.
pretty cool, yeah. I'm supposed to get a name tag.
Yes. We had a system, and then the system went down for maintenance,
Oh,
so we no longer have a system.
okay.
But yeah, if Maddie's by the front, then you'll be able to just get a name tag, write your name.
Good morning, everybody. Please take your seats. We're about to get started.
Hello and good morning, everyone. Hi, I'm Josh Achiam. I'm a safety researcher here at OpenAI, and I'm the main author of Spinning Up in DeepRL. And thank you all so much for being here today at OpenAI's first Spinning Up workshop. For people who are tuning in on the live stream, I'd like to let you know that there is a minor technical difficulty, and so we will not be able to broadcast the slides directly from my computer into the live stream video. So you'll be seeing the screen through the camera. In the event that that's not enough for you to see it clearly, I just open sourced the repo that has the PDFs for these slides. So please go to github.com/openai/spinningup-workshop, and you'll find in the RL intro folder rlintro.pdf, which will be the presentation that I'm about to give. So hopefully that makes it easier for you to follow along. So since this is kind of a new thing that we're doing, I'd like to start today by talking about what it is and why we're doing it and what we hope you get out of it from being here. Education at OpenAI is this concept that, as part of our mission, we want to make sure that we provide for the public good and that we help foster a global community around AGI, which is the thing that at OpenAI we care the most about and are trying to figure out how to make sure happens in a way that's safe and beneficial for all of humanity. So for those of you who aren't already familiar, AGI is artificial general intelligence. The idea is that this is going to be some very powerful AI technology that'll have the ability to change pretty much everything about how we do anything. Something that could potentially do most economically valuable work. Something that could solve tasks that currently only human intelligence is capable of solving. And so we think it's really important that we help people become aware of what AGI is and what the technology that'll likely underlie it is, so that you can think critically about issues that might come up in the future, and also, if you're interested, participate. Because we really need for people to step up and help make sure that this technology is safe and does what we want it to do and doesn't cause anything harmful or detrimental to the world. So Spinning Up is the first thing that we're launching under this Education at OpenAI initiative, and the goal is to help people acquire technical skills in the research topics that we care about. So Spinning Up in DeepRL is a resource that hopefully all of you have seen by now. It contains a number of different pieces, including a short intro to reinforcement learning. So what is this thing that we're doing so much research about at OpenAI? An essay about how you would go about becoming a researcher, if you're interested in joining. A curated list of important papers in the field. So this is particularly important because since this is an emerging field, there isn't really a clear consensus on the best way to learn it or a textbook that completely illuminates the way from start to finish. And a lot of the important knowledge right now is still in research papers. So if you want to find out the most stuff about this, you have to go digging. And hopefully this helps you figure out where to look. Also, a code repo of key algorithms, because for any of you who have tried hacking in this field before, I'm sure you found that there were a lot of very confusing resources out there, really excellent ones, but nonetheless, ones that made non-obvious choices and didn't clearly connect what they were doing to why they were doing it. And so we hope that the repo that we provide in spinning up in DeepRL is part of something to bridge the gap there. And of course, some exercises. So if you want to actually try coding something up, there are a few ideas there for what to do to get you familiar with some of the key pieces of math or algorithms or what kind of bugs you might expect. And so why are we having workshops? So in addition to putting these resources online, we think it's going to really help people if we work with you one-on-one, if we can see you face-to-face and talk with you and have the kind of conversations and share the ideas that just don't come up in the sort of open loop control thing that happens when we put information on the internet. Today, we'd like to have you come away from this with a better sense of what the current capabilities and limitations are in DeepRL, tell you a little bit about what kind of research is out there. So if you want to go and follow some line of thinking, you know what's been done and what hasn't. And we'd like you to actually try building and running algorithms for deep reinforcement learning, possibly for the first time, and show you how to be confident in doing that so that if you want to keep doing it afterwards, you're able to. All right, so then what is deep reinforcement learning? Why do we need it? Why do we care about it? Deep reinforcement learning is the combination of reinforcement learning with deep learning. RL, reinforcement learning, is about solving problems by trial and error. And deep learning is about using these very powerful function approximators called deep neural networks to solve problems. And deep reinforcement learning is just straightforwardly the combination where we're going to have something that's learning by trial and error, and the thing that's getting learned is a deep neural network that's going to make some kind of decision or evaluate some situation and use that ultimately to, in some environment, make decisions that lead to rewards, where reward is just some measure of how good or bad an outcome was. So when would you want to use RL? RL is useful when, for one, there's a sequential decision-making problem. Two, you don't know what the right thing to do in that situation is already. If you have the optimal behavior, say from having watched human experts enough, and you have just a ton of data on exactly what to do in every situation, then you can use the standard tools of, say, supervised learning to exactly get some machine learning system to duplicate that behavior. But when you don't have access to that, or when you suspect that what appears to be expert human behavior is in fact suboptimal in that situation, you may want to try reinforcement learning instead because it could discover things that wouldn't have otherwise been known. And you also have to be able to evaluate whether or not a behavior or an outcome was good or bad. This is pretty critical. So RL is good when it's easier to evaluate behaviors than to generate them or to exactly solve for them. And when would you use deep learning? So the typical paradigm for deep learning is that you want to approximate some very complicated function, a function that usually requires some amount of intelligence. So for instance, if a human looks at a picture of a bird and then knows what species of bird that is, that's a thing that you can't really write down a simple mathematical rule to do. If you want to get a machine to do that, you have to teach it from data. And other problems that you would want to do this for typically have inputs or outputs that are very high dimensional, because it's just quite hard to, from an image or from a video stream or from an audio stream, go to a decision rule without doing some sort of learning in the middle. And also, you typically want to have lots and lots of data, because getting machine learning systems to behave in any reasonable way requires that you give them sufficient examples. And there are tons of problems where this is exactly what you have, and in those domains, deep learning has been very successful at exceeding whatever was previously the state of the art from any other methods that existed before, and creating things that are now standard consumer products. Things that were magic 10 years ago are like completely normal now. The idea that we have super excellent image recognition, facial classification, that you can talk to your phone and it's going to know what you said and it's not just going to come up with some completely random gobbledygook. this is getting better because we're able to leverage this very powerful technology that is deep learning for these problems. And so deep RL is when you have some very hard, high-dimensional problem where you can evaluate behaviors and you want to get a machine to learn how to do it because you can't write down how it should in fact behave. And some very simple examples of this are, say, video games, where you want to go from a computer looking at an image of the screen, so just raw pixels, to a decision rule that scores the most possible points in the game, or behaves in a way which is cool or interesting or exciting. Or perhaps a really sophisticated strategy game, like Go, where really deep thinking and intuition and creativity is necessary to make progress. You can't write down a simple rule for that, but you can learn it with reinforcement learning. Or perhaps you want to control some complex humanoid, some robot to run around and do stuff, or maybe something which is a little less silly, maybe a little more real. Maybe you want to get robots in a factory to quickly learn a new task. When the robot uprising happens, it's because of this. We're very sorry for this research. This was trained, by the way, with an algorithm that was developed here at OpenAI called proximal policy optimization. It's one of the algorithms in spinning up, and if you haven't had any experience with it, then we won't get into it in this lecture today, but any other point in the afternoon during the hackathon, happy to go into detail. So before we proceed into the RL-specific stuff, this is a crowd with a pretty wide range of backgrounds, and so I just want to do a very brief recap of some of the patterns from deep learning. What do you expect when you set up a deep learning problem? What does that look like? What do you have to think about? So we typically talk about it in terms of the language of finding a model that is able to give the right outputs for certain inputs. So in this case, the model is going to be some function of the inputs and parameters, and the parameters are adjustable. We control them, we change them, and we want to change them in a way that's going to make the model behave according to some design specification. The way that we provide the design specification and get the parameters to satisfy it is by setting up some kind of loss function. This tells you, in a nutshell, how good the model is at doing the thing that you want it to do. Usually some measure of just how close the output from the model is to the desired output. And the critical thing about this loss function is that it has to be differentiable with respect to the parameters in the model. And when you have that set up, oh, and of course there's data as well. So you have a bunch of different examples of inputs and outputs, and your loss function reflects how well your model performs across all of them, typically as just some average over per data point losses. So with this setup, you can then proceed to find the optimal model through gradient descent. The idea is that the gradient is a mathematical object that tells you how much the loss changes in response to a change in the parameters. And then you want to, knowing that, change the parameters in a way which is fruitful. That is, it reduces the loss. It reduces the measure of error. So what makes deep learning deep? What is the deep part? It's this idea that function composition is at the core of the models that we make and that we consider. So function composition just means that you have a bunch of different parameterized functions, and the outputs of one are the inputs to the next one. And you can arrange these in many different topologies. We'll call these architectures for neural networks. The very simplest kind is just one where you have an input layer, and then there is a matrix that multiplies that, and then you maybe add some bias to that vector, and then you pass that through a nonlinear activation function. Typically, this is going to squash the outputs from that first linear transformation into something which maybe is in the range from 0 to 1 or 0 to infinity, something relatively simple. But that nonlinearity happens to do a lot of work. And then when you have successive layers, what it allows the model to do ultimately is represent successively more complex features internally. So you might think of the output of each layer as being a new representation of the original input, which has maybe rearranged the information in a way which is easier for some kind of final decision making procedure at the end of the network to make the right decision based on. Aside from that very simple model, there are also substantially more complex ones. So the other two diagrams on this slide are for LSTM networks, so that's in the lower left, and the transformer network, that's on the right. An LSTM network is a recurrent neural network. The idea is that this is the kind of network that can accept a time series of inputs and produce a time series of outputs. And internally, it has some very complicated mechanisms for making sure that information gets propagated effectively across time steps in a hidden state, so that when you make a decision somewhere in the future, you can remember something that you saw in the past, and then you can update the network in a way which is stable and reasonable. The transformer network is substantially more complicated, and it allows networks to do something called attending over their various inputs. So attention is something which is a concept that we can all kind of relate to. When we look at the world, we don't actually process literally every piece of data that we take in concurrently. We particularly attend to whatever happens to be, say, in the center of our field of view, or whatever we're thinking about at the moment, whatever's most urgent. And attention neural networks are able to basically do that when they make some decision on the basis of a lot of data. They can select out the most important pieces of the data for making particular kinds of decisions. And that turns out to be very helpful in practice. A few other things about deep learning, and this is mostly just I'm checking off some boxes. If you want depth on this, I strongly recommend that you go see the Spinning Up essay, where there are a bunch of links to papers and other resources that will give you detailed information about this. But to check off the boxes, we might talk about regularizers. So the idea is that sometimes optimizing your loss function, picking the model that actually gives the lowest value of your loss function, may not be the best thing to do. You may wind up with a phenomenon called overfitting, where you've made your model behave perfectly with respect to the data that you showed it. But then it does a terrible job when it's given any other data, because it learned a decision rule which was entirely too specific. But with regularization, you trade off the loss against something which has nothing to do with performance on the particular task, but just kind of says, hey, cool your jets a little bit. Don't be so avid about satisfying that objective. And then it turns out that regularization actually leads to models that do a better job of generalizing to unseen data. Then there are also a couple of things that make the optimization process smoother and easier. So you might do some kind of normalization technique where internally there's some output in the middle of the network where it's good to adjustably rescale that and shift it around. And that's better than just letting the network do whatever it would have done if you didn't do this kind of normalization. It's sort of spooky, and there are some legitimate complaints inside the community about whether or not we really understand why this helps. But it seems to, so it's worth knowing about. Also, you might use a more powerful optimizer than standard gradient descent. This comes up also in reinforcement learning. Actually, many of the things that we've been talking about in these past few slides show up in deep reinforcement learning, which is why I'm bringing them up. Adaptive optimizers do something special in figuring out how to tune the learning rate, the amount by which you change each parameter at each step of updating, in a way which leads to typically faster convergence. So you get to the optimum point a little bit sooner or a little bit easier. There's also the reparameterization trick, but that's quite complicated, and so we won't actually talk about it. It's on the slide so that you know where to look. All right, that's all the stuff from deep learning that I wanted to talk about. Now on to reinforcement learning. So first and foremost, we have to talk about how do you formulate a reinforcement learning problem? What does that mean? What does that do? What are the pieces of it? How do they fit together? We typically use the language of saying that there's an agent that interacts with an environment. So the agent is whatever thing is making some kind of decision. The environment is wherever those decisions are happening, and the thing that creates the consequences of those decisions. And there's this loop where the environment has some state and has some measure of how good it is to be in that state. That's a reward. And the agent gets to observe the state and possibly the reward. It uses the reward for learning. Whether or not it observes it is a subtle technical detail. But anyway, okay, the agent gets a state, observation, and a reward. And then the agent makes some kind of decision about what action to take. It picks the action, and it executes it in the environment. And then the state of the environment changes. There's a new state of the environment. The agent perceives it. The agent acts, etc. The goal of the agent is to figure out what decisions will maximize the sum total of rewards that it'll ever get. Actually, it's slightly more specific than this, and there are a couple of different formulations that we can choose, and we'll talk about them momentarily. But that's basically it in a nutshell. We want to maximize this sum of rewards that we get. And the agent is going to figure out how to attain that goal through trial and error. So you just don't know in advance what the right thing to do is, so you have to just try things, see what happens, see how much reward you get, and then adjust your decision on the basis of that. So reinforcement learning is about algorithms for doing precisely that. But before we can talk about the algorithms, we have to introduce a bunch of terminology. For those of you who have done the work of going through the spinning up material online, this will probably be quite familiar, and I'm mostly going through it for the benefit of the audience that I expect might watch this in the future as a starting point for this. So bear with me, I'll try to go through this reasonably quickly. But we have to talk about observations and actions, policies, trajectories, rewards and returns, what the RL optimization problem actually is, how we formalize it, and then value and action value functions, and also advantage functions. So there's a whole lot of stuff that you kind of have to know and unpack in order to really fruitfully progress in reinforcement learning, and these are just those central pieces. So observations and actions. A state is something which tells you absolutely everything about the environment. The agent usually doesn't get access to the state. There is usually some stuff that's just hidden from the agent. So what the agent perceives is called an observation. If the observation contains all the information in the state, we call this environment fully observed. If it doesn't, we call it partially observed. And states, observations, and actions can be continuous or discrete. For all of the problems that we care about in DeepRL, the observations are continuous, and the actions might be discrete or continuous. A policy is a rule for selecting actions. There are a couple of different ways that you can get to this kind of rule. We typically classify them as one of two kinds, stochastic or deterministic. A stochastic policy is a rule for randomly selecting an action on the basis of the most recent observation, or possibly preceding observations as well. A deterministic policy is just a map directly from observation to action, and no randomness involved at all. You may be wondering why it would be useful to have a random policy at all, because it might seem like randomness is just sort of dangerous, but actually it can be quite helpful, and there are some very principled ways of optimizing stochastic policies, and it's a little bit harder to optimize completely deterministic policies. There may also be a matter of robustness, in that having a little bit of randomness can make you more robust sometimes to perturbation than having learned a brittle, specific deterministic policy. So now, just to give some sort of concrete examples in TensorFlow, because I assume that most of you will probably have met TensorFlow as your first deep learning library, and if not, PyTorch. And for those of you who are stuck with TensorFlow, I'm so sorry. You probably should have picked PyTorch. I know I should have. But here we are. So in TensorFlow, for a stochastic policy over discrete actions, we might first set up a placeholder for loading in observations, and then we might set up a multi-layer perceptron network, an MLP network. So this is just the most basic kind of feed-forward neural network, the thing that I talked about earlier, which is a succession of linear transforms of inputs followed by nonlinear transforms of inputs. In this case, the linear transforms take you to something of size 64, and there are two of them. And then the activation is a tanh activation. So this gets you to a range of -1 to 1 in a nice, smooth way. And then we produce logits based on the output from that piece of the network. So logits are basically something that precedes having probabilities for particular actions. If you take the softmax of the logits, if that's not a function you're familiar with, I recommend looking it up. It's just something that exponentiates all the logits and then divides by the sum of those exponentiated logits. So it normalizes the distribution to being a probability distribution. All the entries have to be greater than 0 and sum up to 1. So we get logits, and then we get actions by using tf.multinomial to sample something stochastically, assuming that the probabilities are based on taking the softmax of those logits. You can ignore the squeeze. That's just there for making sure that certain things actually work. Uh, and then in a deterministic policy, let's say we have a continuous action case. So we want to output a vector of actions where each entry can be any real valued number. We will just go from observation to network to a final layer, which is just going to be the actions. All right, so that's policies. Let's talk about a trajectory. A trajectory is a complete sequence of states and actions through the history of an environment. The agent starts in a state, takes an action, then there's a next state, next action, etc. The first state in the environment is sampled from some previous distribution over starting states, and then afterwards, state transitions are going to be either deterministic or stochastic, but there's just some rule in the environment that given the current state and the current action, whatever action the agent took, picks what the next state is. A trajectory is also sometimes called an episode or a rollout. You'll see this terminology used completely interchangeably, so just be aware that's out there. I'm so sorry, in every new-ish field, a lot of terminology confusion where different people in different areas of academia worked on it for a while and used different terms, and then in the end we're left with just a weird mishmash. Notation too. You're going to see some notation where states and actions are notated by S and A. And then in code you'll see some places where it's X and U, and this is because of the ancient eternal conflict between the control theorists and the reinforcement learning theorists, and we're just stuck with it now. So that aside, let's talk about rewards and returns. So a reward function is going to map from states and actions, or states and actions and possibly next states, onto just some number that tells you good or bad. Positive is good, negative is bad. The more positive, the better. And you have to, if you're a designer setting up a reinforcement learning problem, you have to pick what that reward function is going to be. So you want to make sure that you incentivize the stuff that you want to have happen and disincentivize stuff that you don't want to have happen. So as a very simple example, suppose that you want a robot to run forward, but you don't want it to waste a ton of energy. So maybe you will give it a reward proportional to its forward velocity, but you'll penalize it proportionally to the sum of the action magnitude. So you'll discourage superfluous actions. The return of a trajectory is going to be some cumulative reward along it. We have two ways of formulating this, and what you're going to find in deep reinforcement learning implementations is that we're going to completely conflate which problem we're trying to solve with the other. But the finite horizon undiscounted sum of rewards works when you have a finite horizon. It doesn't work when you have an infinite horizon, because if you have an infinite sum of things, it might diverge, unless you do some kind of discounting. So in this other case, infinite horizon discounted sum of returns, you have a discount factor, gamma, between 0 and 1. And that's how you downweight things that happen in the future. This makes sure that this is a reasonably well-defined quantity. But why would it make sense to discount things? You probably would rather someone tell you that they're going to give you $100 today than $100 in 100 years. Right? Like, it's just good to get rewards up front. Then there's the reward to go. This is closely related. It's basically just a measure of return starting from a particular time step or state. So the reward to go from some point in time is just the sum of rewards that'll happen after that point in time. And now we can talk about the reinforcement learning problem. Just formally, we're going to set up a performance measure for a particular policy pi, j of pi, which is the expected value of return for whichever formulation we've picked, according to a distribution over trajectories in the environment based on the choice of policy. So what that means is that, again, start states come from a starting distribution. Transitions in the environment are based on something in the environment, that transition distribution P. And actions will come from the policy conditioned on the observations of the states. And we want to find the optimal policy pi star which maximizes this. Now we have to talk about value functions. So value functions are measures of how much reward you expect to get from a particular state or state action pair, assuming that you're going to behave a certain way. So we have the on-policy value function and action value function, v pi and q pi, which respectively tell you how good it is to be in a particular state and how good it is to be in a particular state action pair, assuming that forever after being in those places, you act according to the policy pi. And then there's also v star and q star, same thing, except if you were to act according to the optimal policy. It's great to know q star, as we'll talk about momentarily. Value and action value functions are connected. The value is just the expected action value, expecting over what action you might take according to the current policy. And the advantage function tells you how much better a given action is than average. And it's just the difference between Q and V. These value functions satisfy recursive Bellman equations. These are super important, and they're the foundation of a bunch of algorithms, so they're really worth knowing and kind of just worth grappling with. I think that these can be particularly tricky at first. I remember the first time that I met reinforcement learning, I was just so turned around and lost by these. The notion that there was going to be this recursive equation where the definition of a thing depended on itself was quite confusing. But it's worth just hitting your head on for a while until it makes sense. But what it's saying is that the value of being in a particular place is going to be as good as whatever reward you get for being in that place, plus all the rewards that you'll ever get for all the places you'll go afterwards. Now, why is it great to know Q star? Q star tells you if you're going to act according to the optimal policy forever after you started in this state and took this action, and we don't care what policy this action came from, how well will you do? So that means that if you want to do the best you possibly can do, all you need to know is what action maximizes Q star in a particular state, and then take that action, because that's going to be the best action in that state. And then afterwards, you've assumed that you're going to do the best that you can ever possibly do. So if you have Q star, you basically have the optimal policy. So this is going to lead us ultimately to the two different kinds of algorithms in reinforcement learning for control, where in one case we'll try to directly optimize a policy, and in the other case we'll try to find Q star. Now, if we want to find Q star, we have to set up a function approximator for it, Q theta, which we'll represent by some kind of deep neural network. And we're going to want to measure how good is it at approximating Q star, and this is what that recursive Bellman equation is going to be really helpful for. Because the beautiful thing is, we don't need to have acted according to the optimal policy to check how well Q theta fits that Bellman equation. We just need a bunch of examples of state, action, next state, and reward tuples. And if we have enough of those over enough of the environment, then we can probably do a pretty good job of fitting Q theta based on that Bellman equation, based on maybe this mean squared Bellman error, and then use that afterwards for control, which is having a decision-making rule. By the way, I apologize if anything has been confusing about my using sort of the terminology of control interchangeably with the terminology of reinforcement learning. When I say control, I mean having the best policy. So, now, what kinds of RL algorithms are out there? Behold, a taxonomy, which is much more restrictive than it looks. It looks very pretty and it looks very definitive, but it's actually masking a lot of subtlety and detailed choices, and the fact that there's actually a lot more bleed over between these things than you might expect. But at a very high level, this is a useful picture to start with, that we have two different kinds of RL algorithms. Ones where we have access to the model of the environment and ones where we don't. So what that means, a model of the environment is something which tells us if we're in a given state and we take a particular action, what's going to happen next. The model would predict what the state of the environment will be after that. And that's really useful, because if we can forward simulate the environment, then that's extremely helpful for evaluating our current policy. It's extremely helpful for figuring out what a better action would be than the one that we might want to take. So if you don't have a model, you're quite limited. You just have to figure out how to do well based on experiences that you've seen, your direct interactions with the environment. You don't get any other information. But if you do have a model, it's quite potentially powerful, although, as we'll discuss, the methods for model-based reinforcement learning are not quite as mature so far as the methods for model-free reinforcement learning. So now, okay. That last slide was just a ton of acronyms, maybe not that insightful. Let's talk about what these algorithms are doing. There are three key pieces in any reinforcement learning algorithm. For one, you're going to run the policy in the environment. You're going to actually try things and get to some signal, error or otherwise. And then you're going to have to reflect and evaluate whether or not those decisions were good ones, whether or not those actions were the right ones. You have to figure out how good your current policy is so that you can use that information to improve it. So you run the policy, you evaluate the policy, you improve the policy. And there are a bunch of different ways of doing that. And we'll go into some depth about how different algorithms go about doing that. So let's start with policy optimization. Minor interlude. In the chat last night, I surveyed people to see what they were interested in. I asked if people were interested in math. There's going to be some math. So first, at a very high level, zooming out, 10,000-foot view, in policy optimization, we're going to run the policy by collecting complete trajectories or snippets of trajectories based on our current stochastic policy. And we're going to explicitly represent that stochastic policy with a neural network that perhaps gives the sufficient statistics of the action distribution or something else that we can use to derive that and sample from it. And then we're going to evaluate the policy by figuring out the on-policy value function and advantage function. And we're going to evaluate those things for all the states and actions in the trajectories that we sampled. And then we're going to improve the policy by making it more likely that we take the actions that led to higher advantage, and making it less likely that we take the actions that led to lower advantage, less likely that we take the bad actions. How do we do that? We're going to have to talk about some math. Now, I realize there's a chance that most of you maybe weren't expecting that we would be doing any kind of deep mathematical excursion, but if there's one thing that I want you to take away from today, aside from just being excited about DeepRL, it's a realization that there are some limitations to what DeepRL can currently do, and that this is not really 100% done as a technology where you can just apply it to a problem without really thinking about what it's doing under the hood and get a good solution. It's not a black box technology yet. So if you want to try DeepRL on a problem and grapple with getting it to work, you do have to kind of understand what's going on under the hood, and that means taking a look at some of the gory mathematical details, understanding how they connect, and forming an intuition for how those details will shape the failure modes of your algorithm. So what we'll talk about, we're just going to talk about vanilla policy gradient. We're going to talk about how you derive the policy gradient and a bunch of different equivalent expressions for it. And then we'll get to the pseudocode for the sort of standard version of vanilla policy gradient, which includes maybe a few more tricks and details than the very most basic vanilla version. Apologies for the choice of words there. But all of this stuff is critical to understanding more advanced policy optimization algorithms like TRPO and PPO. We won't be covering them in these slides, but again, happy to talk about them offline during the hackathon. So, in policy gradient algorithms, what we want to do is we want to find some kind of expression for the gradient of the policy performance with respect to the parameters of the policy, and we want to just directly gradient descend on those parameters. So we're going to move the parameters in the direction that increases performance. And is this going to be easy or hard? Well, if we just try putting the gradient onto the policy performance, we run into a problem. All the parameters are down here in the distribution. They're not inside here, where we would like them. If we want to get something that we can actually use, we'll have to do some messy work to bring the gradient inside of an expectation, which we could then form a sample estimate of. So, step one to getting the gradient symbol somewhere helpful. We're going to recognize that this expectation can be rewritten as an integral, going through all of the events in trajectory space, every possible trajectory of the density, the probability mass or density for that trajectory based on that policy, times the return that you would get for being on that trajectory. And now we can bring the gradient in because the limits of this integral don't have anything to do with the parameters. And then we apply the log derivative trick. So this is a really helpful mathematical trick, comes up all over the place in deep reinforcement learning. It's basically just this notion that the derivative of log of something is 1 over that something times the derivative of that something. And we rearrange it slightly. But it lets us go from the gradient with respect to theta of p to p times gradient log p. This is great, because now we have an expectation again. We have an expectation based on trajectories sampled according to the current policy. So if we have that data, we can make a sample estimate. Could you repeat that? Certainly. So the very nice thing here is that what we did after bringing the gradient inside the integral and doing this log derivative trick is that we now have something which is an expectation again, because we're integrating through all possible trajectories of the probability density associated to that trajectory times something which is a function of that trajectory. So this is an expectation, and we can form a sample estimate of it that we can use in a practical algorithm. But we're not completely finished yet, because we still have to talk about what's the gradient of that log probability for a trajectory. How does that depend on the parameters of the policy? So let's go back to the picture that we had in the beginning. There's a starting state, which is drawn from some distribution based on the environment. And then after that, the agent picks an action based on pi theta, and it has probability pi theta a given s for time step 0. Then the environment picks the next state according to whatever distribution it has over next states, given your most recent action and the most recent state. By the way, this is something that I glossed over earlier, slightly more formalism details that you don't quite need to know. But this is called the Markov property. This notion that picking the next state only depends on the most recent thing that happened and doesn't depend on the past before it. That's the Markov property, and you'll find a whole bunch of math if you go digging for it. But you don't have to for this at the very least. So then what we have is that the probability of the trajectory is going to be just the probability of that first state times the probabilities of each transition and action selection that happens afterwards. So we get that expression up there at the top. And now if we want to take its gradient of its log, we just pretty straightforwardly compute. First, the log of that thing turns that product into a bunch of sums. The gradient goes through the sums. And now all the terms that are based on distributions from the environment have no dependence on the parameters of the policy. The environment doesn't care what the policy is. It's just going to behave in whatever way it does. So those have no dependence on the parameters. Those derivatives are 0. And what we're left with is just something which is a sum over time steps of gradients of the policy. The beautiful thing is, because we control the policy and we have explicitly represented it as a neural network, and we can compute all of its gradients, this is a thing that we can calculate. So now we're at something where we can, in fact, calculate a sample estimate of this gradient of policy performance and use that as the basis for a gradient ascent algorithm for improving performance. But it's not good enough. We're not done yet. Yes? The function capital E. So this capital E is an expectation. And if we want to form an estimate for the expectation, so we're not going to compute the expectation exactly. What we're going to do is we're going to see what happens for a bunch of different trajectories that are sampled according to the distribution specified in that expectation. And then we're just going to average them. And in the limit, as we have an infinite amount of data, that sample average becomes exactly equal to the expectation. Yes?
This may be 10 steps back, but can I just think of a gradient as a derivative, or is there a meaningful?
Absolutely. Absolutely you can. So it is a bunch of derivatives of the final output with respect to each one of the parameters, right? Because there are many inputs to this function, and we're going to have a derivative with respect to all of them. Yes? I'm sorry, can you repeat the question? Yes, can we tie this explicitly to reward? So inside the expectation here, we have R of tau. So that's the return measure that we've chosen, whichever one we picked, either the infinite horizon discounted sum of rewards along the trajectory tau, or just the finite horizon undiscounted sum of rewards. So that R of tau is the sum of all the rewards in that particular trajectory. And that's actually why the variance of this is going to be so unnecessarily high. There are going to be a bunch of terms in this sample expression, actually just in that expectation, which have expectation 0. On average, they're 0. They don't contribute anything. But we sample them anyway, and the samples will have noise on them, and so we'll just wind up getting the noise. We won't get much signal from them. So can we eliminate a whole bunch of terms? Yes, we absolutely can. The intuition here is that if I give you a reward in the past, and you want to update the action that you just took. Really, what you care about for figuring out whether or not the action that you just took was good or bad are the consequences of that action. You don't care about what preceded it. That action and what preceded it are almost completely uncorrelated. You're not going to get anything by updating the likelihood of that action based on an old reward. So that in expectation is going to be 0. And knowing that, we can now expand out this return measure, and we're going to look at this in the finite horizon case, just for simplicity, but this analysis also extends to the infinite horizon case. So we now have a sum of grad log probs of the policy times the sum of rewards. We're going to pull the sums out of this expression so that we can just look at a policy update at a particular time step times a reward from a different time step. And then based on that thing that we asserted above, we're going to drop all the terms that are inconsequential. All of those are 0. And so what we're left with, after we take away all the ones where t greater than t prime, we're left with this sum over the time steps for the policy, times a sum over time steps for rewards that goes for all of the time steps after the corresponding policy time step. And then if we bring that back in, what we're seeing now is that we want to, for each time step, adjust the probability of the action from that time step in proportion to the sum of rewards that came afterwards. Only the consequences of an action will affect its update. Yes? So it's not that you don't consider past actions. The sum over here in the beginning runs over all time steps. So every action is going to get some update. It's just a matter of which rewards are used in figuring out the update for that action. And it should only be the ones that were consequences of it. Yes?
So the Bellman equation,
Yes.
considers the future, right? In a way, like the future rewards I'm going to get. But here we don't care about the future. Like, why? What is the difference?
Well, we do care about the future, right? Because here we have a sum of rewards after a particular time step. All the rewards in the future from that time step.
But the expectation is 0, like the beginning, for t greater than t prime.
So that expectation, that's just saying that an action that happens later shouldn't be affected by a reward that happened before it. It should only be affected by the rewards that happen afterwards. So in the next slide, actually, we'll see how this expression that we have down here at the bottom connects to the value functions. So what we currently have is what I'll call the reward to go policy gradient, because what we're doing is we're adjusting the probabilities of actions proportionally to the reward to go. What we're going to do now is go from that into an expression that has q pi, the action value on policy for a state action pair, instead of that reward to go. And this works because you can break up the expectation. So first we're going to pull the sum over time steps out of this. And then this expectation over trajectories. This is sort of subtle and maybe a little mathier than we can go into detail on here. But I recommend that you go look on the Spinning Up website in RL Intro Part 3. There's a link separately to a proof about this. But if we think about the average thing that's going to happen over all trajectories, that's going to be equivalent to the average thing that happens over all of the cases of something with the first t time steps of the trajectory, where inside of the expectation, we've moved all the stuff that happens in the future. And we were able to move it inside past this one, because this only depends on time step t. This doesn't depend on stuff after t. So only this stuff is going to be affected by averaging over the future. And then it turns out that that expression, the average sum of rewards that you get starting from a time step, assuming that the state and action for that time step were fixed, that's exactly equal to the action value. That's exactly saying how good is it to be in a particular state, take a particular action, and then forever after act according to a particular policy. And now we have this expression for the policy gradient at the bottom. We're most of the way through the math. Okay, but what is a baseline? A baseline is a really important thing because it's another tool in our arsenal for taking a policy gradient expression and turning it into something which is lower variance, more likely to be useful for producing a good update to the policy. And it's also the namesake for OpenAI baselines. Well, let's say one of them. It's a couple of things. But we have a expression here at the top, which I claim is basically true, which is that the gradient, the policy gradient, is the thing that we had before, but instead of Q, we subtract out some function of state, some function B of ST, and I claim that in expectation, it works out exactly the same. And so there's a short proof here for that, which is that if we look at the expectation for that part of it, what happens if you take the expected gradient of the log probability of an action in a state times some function B of ST? The B doesn't have anything to do with the action. So it's a constant with respect to this expectation. So we pull it out. And then what we're left with is an expectation over actions, which we'll rewrite. And now we have it in probability times grad log prob. We're going to reverse the log derivative trick from earlier. So this is now an integral over actions of the gradient of the probability of that action. And we can pull out the gradient. So we're just sort of reversing the procedure from earlier. This thing, this integral over all possible actions of the probabilities of those actions, that's just going to sum up to 1. That's just saying probability distribution is normalized. All of the chances together have to come out to equaling 100% if you sum them up. And the derivative of a constant, since that's a constant, is nothing. Constant has no rate of change. So we get 0. So all of the terms of grad log prob times the baseline in expectation are 0. So we're free to add this baseline without changing what the policy gradient is in expectation, but we can pick it in ways that are fruitful and make the estimate better. So the typical thing to do is to pick the baseline to be the value function. And this leads us to kind of our final sort of ultimate form of the policy gradient, the form with advantage functions. And why is this good? Why is this good? The advantage function says how much better an action is than average. Why would you prefer that over just how good the action is? Well, let's say you have 2 actions. One gets you $100, one gets you $101. You only sample the one that gets you 100. Now, when you're trying to update your policy, you can feel really great about that. Oh man, 100 is a big number. I feel great. I'm going to double down on that action. You're acting suboptimally. If you had been picking 50-50, on average you would have gotten $100.50. And you would have realized that the advantage of taking the action that you picked, $100.50, 100 minus $100.50, you lost 50 cents. You should pick the other action. So you prefer to use advantages to figure out which actions to increase the likelihood of, as opposed to just Q values. All right, summing it up, we have these 4 different forms of the policy gradient. They're all tightly connected. We care about the last one, but to get to the last one, we had to go through the pain. But now that we've all gone through that pain together, you're stronger. You can go and you can implement this, and it'll work, and you'll know why it works, and you'll feel good about that. And if it breaks, you can fix it. All right. So then just to sum it up, this key concept, we want to push up the probabilities of good actions, push down the probabilities of bad ones. And also, importantly, that expectation requires trajectories sampled from the current policy. So this is the concept of being on policy in reinforcement learning. That if you want to update your policy, you have to use data from that policy. You can't use data from some other policy unless you appropriately reweight it. But reweighting data is complicated and really tricky, so it's sort of preferred to not do it unless you are trying to build something new and cool and super sample efficient, and you're willing to spend a lot of time and effort doing research on making sure that it actually works. But okay, so the policy gradient expression gives us the policy improvement step. Coming back a bit. Oh yeah, sure. Mm-hmm. The question was, how do we know what the average reward would have been so that we could figure out how to make the advantage function in the first place? Do we compute it as we go? And actually, that's exactly what the next slide is about, which is how do we do that business of policy evaluation? How do we find an estimate of the advantage function which is actually good and reasonable if we just have a bunch of data? Where do we get the value function that we might use to subtract out as a baseline? And the idea here is that we're going to learn it from data. And typically, it's going to be by regression. So this will be a subroutine that you'll find in most policy optimization algorithms where you're going to have a value function approximator, another neural network, and you're going to, at each epoch of the policy optimization algorithm, update the value network to try to match the empirical returns that you saw. So for a particular state, the value should be more or less the sum of discounted rewards that you saw after then. And then when you have the value function approximator, you can use that to estimate advantages. And we'll talk a bit about estimating advantages from value function approximators on the next slide. But first, you may have noticed that I pulled a fast one on you, which is that we went from, in all the preceding slides, dealing with the finite horizon undiscounted case. And then here in our optimization problem for learning the value function, I've dropped in discount factors. Why is that? The answer is because everyone does it. This is where there's not a particularly good reason, in my opinion, that this happens. But pretty much every policy optimization algorithm that I'm aware of, every single implementation uses discounted value functions and advantage functions, but then treats the policy optimization part as undiscounted. It creates some bias. It seems to work. Shrug.
So what if you don't do the discounted one?
It's perfectly reasonable to do that. So it sometimes seems to be helpful to set the discount factor to something a little smaller than 1. So keeping it completely undiscounted would be gamma equals 1. For whatever reason, with some optimization problems, or some RL problems, it's a little bit harder if you pick gamma equals 1 than gamma 0.95. And I can't say that there's a particularly good reason for this. I would speculate that, like in the beginning of training, if you pick a very high discount factor, those empirical returns will be very noisy. And if you choose a discount factor less than 1, what you're going to do is you're going to attenuate some of the noise. You'll bias that sum of rewards so that whatever happens soonest matters most. And if you happen to see a few positive rewards in a row, then you'll latch onto that. Whereas maybe because of noise, if you had really paid attention to everything out to infinity, you'd have just gotten a bunch of positives and negatives and positives and negatives, and they would have canceled out.
So it's essentially a regularized sort of.
I think it's okay to think about it like that, yeah. Yes, that after a certain point, the trajectory just ends, you get to time step t, and then it's over. That's finite horizon. Infinite horizon, you go out to infinity. All right, so then how do we calculate the advantage function given data from trajectories and a value function approximator? So a thing that I want to introduce here is this notion of n-step advantage estimates. So what you're going to do is you're going to have a thing over on the left side that approximates q pi and a thing over on the right side that approximates v pi. So this thing for q pi, remember that that's supposed to be an estimate for how well you'll ever do if you start in a state, take an action, and then act according to the policy forever after. You can just use the empirical return, the reward to go from that state, as a sample estimate of the expected value, which is the q value. But in an n-step advantage estimate, what we're going to do is we're not going to go all the way out to the end of the trajectory in that sample estimate for q. We're going to go n steps in and then use the value function approximator to assume what's going to happen for the rest of it. And this corresponds to a decision about how much bias or variance we find acceptable in this advantage estimator. So if you pick n equals 0, then your advantage estimator in that case would be just the reward plus gamma times the value function approximator for the next time step minus the value function approximator for the current time step. And that's going to be very high bias because whatever's wrong with your value function is then going to be wrong with your advantage function. But it'll be really low variance because the only thing that's going to have variance to it is the reward and the stochasticity in the next state transition. But if on the other hand you pick n equals infinity, so for the Q approximator, you just take the exact sum of rewards that you got in the real trajectory, and then at the end you subtract out the value function at st. You're going to accept all of the variance that's in the environment. But the nice thing is you don't have bias informing your policy gradient estimator with this, because in expectation, the Q part is going to be exactly Q in expectation, and the V part, recall that was a baseline that we added with a guarantee of no bias in the policy gradient. So on expectation, that part falls out, and it's fine. So the bias variance trade-off is typically mitigated through what we call generalized advantage estimation. So this is a way of interpolating between all of those different possible choices of n-step advantage estimate, where we use a factor called lambda. So this is sort of like another discount factor as the interpolation variable. And it's a hyperparameter, and you choose it in each implementation that you make. And it's generally good to set it somewhere between like 0.9 and 9.7. Usually it's a set it and forget it in my experience. I can't think of very many cases when I saw a substantial difference in algorithm performance from adjusting it beyond that kind of narrow range. If you set it equal to 1, then you'll get exactly the case of the n equals infinity, and if you set it to 0, then you'll get exactly the n equals 0 case. So it's good to kind of leave it in the range where it's putting a little bit more weight on the real empirical returns than the biased value estimator, but not all the way to the extreme. Okay, at long last, I give you the pseudocode for the full vanilla policy gradient algorithm that incorporates everything that we've talked about so far. What we're going to do is collect a set of trajectories by running the current policy in the environment. And then we'll compute the rewards to go so that we can use them as targets for the value function approximator. We'll compute the advantage function estimates with any method of advantage estimation, but typically generalized advantage estimation. And then we're going to use those to estimate the policy gradient. With that, we take a step of gradient descent. We might use an adaptive optimizer like Atom to accelerate the rate at which we learn. And then we're going to do the supervised learning problem of trying to get the value function approximator to match the empirical returns. And that's how we learn our value function, and then we loop. That's vanilla policy gradient. Yeah?
Could you talk about the network of the value function and the network of the actual policy? Is that typically the same? Is that
Absolutely. So yes, usually you will pick networks of the same size for policy and value function. In cases where the environment is partially observed, you may want to have a single core recurrent neural network that's going to be able to remember past information and then give that core neural network separate outputs for policy and value function. And then you'll train that jointly. And it gets a little bit complicated because I can't say that there's any good work in RL theory that I'm aware of that reasons about how it alters performance for the final policy to be simultaneously optimizing with respect to both objectives on the same model. But that's what you would do in that situation. So yes, typically they'll be about the same size unless they're actually sharing parameters, and then they're sort of the same model. Yes? Does the choice of initial policy affect convergence? Wonderful question, and sadly, in a lot of cases, yeah. So this is part of what goes into my saying that deep reinforcement learning is not a technology that's ready to be used as a black box yet. So when we do experiments in deep reinforcement learning, we typically run the same exact experiment with different choices of seed for the random number generators. And what we find is that the seed, which in the beginning of the algorithm only changes the initialization of the policies and value functions, happens to matter quite significantly. Some seeds learn, some seeds don't. Some seeds learn much more slowly than others. And there's no particularly good reason for it. We are generally quite heartened when we find an algorithm that appears to be robust to initial conditions and where the average of the learning curves is quite narrow. We think that's great, and it doesn't quite happen as often as we would hope. All right. Do we have any other questions about policy gradients? So in the bottom right-hand corner there, that says 47 out of 63. I may have slightly miscalibrated how long parts 1 and part 2 were relative to the initial time slots of 45 minutes and 1 hour respectively. This is by far the longer one. But since we've been at it for an hour, I think this is a good point to take a 15-minute break, and we'll pick back up to discuss Q-learning after coffee. Thank you so much.
We will. We will be resuming with Joshua Achiam's introduction to RL in 2 minutes.
Hello? Hi, everyone. We're about to get started for the second part of Intro to RL. And just as a heads up, I prepared entirely too many slides for the hour and 45 minutes that I was scheduled to speak. Please bear with that because, this is the first time we're doing this, and so I'm still getting calibrated on what we can get through in that amount of time. But everything that I don't cover by 11 a.m. when I hand over the mic to the next speaker, I'm more than happy to share with you later today during the hackathon. So in particular, the material that I expect that we won't quite get to will involve an overview of what's been accomplished recently in deep reinforcement learning and where the challenges and limitations are and what the research horizons look like on those limitations. But before we do any of that, let's continue our discussion from earlier and talk about the next major family for algorithms for deep RL for control, which is to say Q-learning. So there are a lot of algorithms that fall under this umbrella. Deep Q-learning was one of the first algorithms that really made deep reinforcement learning viable and popular. Speaking from personal experience, I just started my graduate student career in 2014 when I heard about the Playing Atari with Deep Reinforcement Learning paper. I was just becoming aware of topics in AI and AI research, and that completely and totally blew my mind. It was the most exciting thing that I had ever seen, that a computer could just figure out from looking at what was happening on a screen how to behave, how to play a game, how to do something that I thought required some human spark of understanding and capability for joy. And the computer had it. It was beautiful and amazing, and it made me want to study this and participate in taking this technology all the way from where it was at that point to what it could be in the future. Anyway, Q-learning. So back to this RL loop that we have: run policy, evaluate policy, improve policy. In Q-learning, you run the policy by taking a step in the environment either randomly, so there's going to be some stochasticity in what you do, or you're going to act in a way which is called greedy with respect to your current Q function approximator. So remember, what you're trying to learn is Q star, the optimal action value function. And if you happen to have Q star, then whatever action is the maximum, or maximizes Q theta in a particular state is the best action to take. But when you don't, in fact, have Q theta equals Q star, then the maximizing action probably isn't great, so exploring a little bit by acting randomly is going to help you. And then once you've taken that step in the environment, so you send an action to it and you get back a reward in a next state, you store that transition, state, action, reward, next state, in a replay buffer. You save it for later because you're going to use it for learning how to evaluate the policy, which is to say updating Q theta to try to have it fit that Bellman equation. And once you have that, the policy improvement step is just looking into Q theta and saying, what's the action that maximizes this? Policy improvement is basically implicit in Q-learning. And we're going to structure our discussion about Q-learning around the original deep Q networks algorithm. But pretty much everything in this discussion is quite general for Q-learning methods because they all kind of share this common DNA of you take a step in the environment, you take some gradient descent steps on your Q function to minimize the mean squared Bellman error, and you use the techniques that we'll describe in a minute, experience replay and target networks, to stabilize the learning procedure. So, Q-learning updates by bootstrapping. So what is that? It's this notion of how are we actually going to fit Q to that Bellman equation. So we talked about minimizing mean squared Bellman error, and it's a useful picture to start with, and so I'm going to keep using that terminology, although in a few slides I'm going to tell you something completely different and ask you to ignore this and pretend you never heard it. But this is where all the papers start, and this is where all the tutorials start, so it's good to familiarize you. What you're going to do to update Q is set up this loss function where you're going to average or sum over data from your replay buffer D, and you're going to have these transitions, state, action, next state, reward, and you're going to regress Q theta against targets Y, where those y's are obtained basically from that Bellman backup, from that Bellman equation, as the reward plus the q value in the next time step. And this is based on the Bellman equation for the optimal action value function. So it's going to have that max over next actions, which is to say that it's going to assume that, if q theta was optimal, if it was q star, then whichever action maximized it in that state would be the best one to take, and that would be the best value there. So interestingly, you don't propagate gradients through y, even though y has a dependence on the parameters of q theta. And the reasons for this are kind of mathy, so we'll get to them in a bit. Okay, getting this to work. So there are two main techniques that I mentioned. There's experience replay and there's target networks. The idea behind experience replay is just that you want to use a really wide distribution of data for training your Q function. You don't want to fit it really well to a very narrow region of transition space, because if you do, it's not going to be good anywhere else. And if it's not good anywhere else, you're not going to be able to bootstrap it to the correct values, even in the places where you've been trying to fit it. You'll get nothing which is actually useful for control. So experience replay helps you broaden that data distribution, fit Q well everywhere, get something which is good for control. Target networks. So bootstrapping with function approximators is super, super, super unstable. That thing that we said on the previous slide where the y's depend exactly on the current thetas, actually throw that out, can't do that, that won't work. If you try to do it, what's going to happen is typically that Q values will explode. They'll go to something really large or really negative, and that'll happen really fast. You won't be able to control it. Even with reasonably well-tuned learning rates, you probably won't be able to stop it. So instead, what we're going to do is we're going to have some target network, Q theta targ, and we're going to make sure that that network tracks reasonably closely to Q theta, but there's going to be a lag so that it updates more slowly. So that if you make an update to Q theta, which pushes a Q value too high or a little too low, then that doesn't immediately propagate into Q theta targ, and therefore does not propagate into the bootstrap. So this Y thing, we're going to call this the bootstrap. And then this tamps down on instability. Granted, why, if Q learning is so horrifically unstable, would we want to do it like this in the first place? Why wouldn't we just differentiate through with respect to that bootstrap? And the answer is that if you differentiate all the way through, it tends to not work that well. And the reason that this thing does, the reason that it works well if you do this kind of bootstrapping approach, as long as you take some appropriate precautions, has something to do with the theory underlying Q learning, and we'll talk about that in a few slides, but not quite yet. You're spared for now. So also, another note, in deep Q networks, the particular algorithm that we're talking about right now, action space matters a lot. So what we did in describing that bootstrap, we had a maximization over actions of the Q function. If you have a Q function that accepts as input a continuous state and a continuous action and feeds that into a deep neural network, trying to figure out the action that maximizes the Q function output is really hard. That would be a non-trivial optimization problem, an expensive subroutine. So if we want to be able to get that max over actions, that's a case where we won't really be able to do it. So DQN will apply specifically to the discrete action case, where we're able to use a network architecture that instead of taking a continuous action as an input at the bottom of the network, emits action values for each possible output, or for each possible action at the end of the network. So a single observation goes in, and then K action values come out, where K is the number of actions, one for each action. And then, because there's just a finite number of them, it's very easy to figure out which action maximized the Q value. We can compare all of them directly. So now we can talk about the pseudocode for deep Q learning. This is relatively straightforward, based on the stuff that we just described. There's one thing which is a little more specific than what I mentioned, which is this business of epsilon greedy exploration. So I mentioned before that you're going to explore by sometimes taking a completely random action and sometimes taking the action which is greedy, which maximizes your current Q function approximator. So epsilon greedy is a strategy for doing that, where with probability epsilon, where epsilon is going to be something small, you'll pick a completely random action, so uniform random over the k different choices. And with probability 1 minus epsilon, most of the time, you'll pick the action that's greedy with respect to your current Q function. So that's the run policy step. And then after you store that transition into the replay buffer and anneal epsilon, because over time, you want to explore less and exploit more. You want to rely on the policy as it gets better. After doing that, you're now going to evaluate the policy by learning Q star from the data, by improving Q theta to be a better reflector of Q star. So that's exactly the step of gradient descent that we described, which is that you sample some transitions from your replay buffer, from your experience replay memory, and you compute the bootstraps for those transitions. And there's a special case for if a transition ended in a terminal state, which is that we don't give it a value after that particular time step. And then we use those y values in our bootstrapped Q value regression, update the parameters, and then every once in a while, with some frequency, we'll copy over the parameters of the main Q network onto the target network. So that's the target network lagging the Q network, ensuring stability. And that's deep Q learning in a nutshell. This algorithm kicked off everything. I mean, there's a whole bunch of stuff that preceded it. You can't really point to any one moment in the history of a field that, had no precedent. Before this, there was neural fitted Q. Before that, there was Q learning with linear function approximation, and there were all kinds of algorithms for trying to get things to work with nonlinear function approximation, like deep neural networks. But this was the one that got a lot of people really, really excited. So anyhow, caveat emptor. Buyer beware, this can break. This will not work on every problem out of the box. You'll try it in some places, and it just won't work. You'll fiddle with hyperparameters, and it still won't work. You'll try some tricks to stabilize it, because there are pretty much infinity tricks to make deep Q learning better at this point. And some of the time, that still won't work. So this picture here is from a recent paper which I really love and which I strongly recommend that you take a look at if you get interested in seeing some analysis of failure modes for algorithms in deep RL. It's called Deep Reinforcement Learning and the Deadly Triad. The Deadly Triad is a set of traits that deep reinforcement learning algorithms might have, which are known to occasionally cause divergence and to create substantial obstacles to theoreticians who would like to come up with algorithms that have provable convergence guarantees. So the Deadly Triad consists of function approximation, off-policy learning, and bootstrapping, which are exactly the three things that deep Q learning relies on. We have function approximation in the form of neural networks, we have off-policy learning in the form of experience replay, and we have bootstrapping in the form of using the target network with a one-step backup as the regression target for Q. And so deep Q learning works a whole lot of the time, and then some of the time it just doesn't. So in this set of experiments, what the researchers did was they examined deep Q learning and a few variants of it, ablating on whether they would include a target network. So here, this Q does not have a target network. The regression target that it uses is exactly based on Q theta, not Q theta targ. And tried it with a target network, and then tried a couple of other tricks that relate to how you use the target network to possibly either estimate the value in the bootstrap or select the action in the bootstrap. And those are tricks that are known to potentially help. They looked at all these different cases for many different Atari games as the experimental test bed, and they clipped the rewards in the environments into a certain range so that they knew exactly, mathematically, what the ceiling for possible real Q value would be. They chose it to be 100. And they looked and saw over all the experiments that they ran, how often did the maximum absolute learned Q value in an experiment exceed the threshold, which they knew was the real, true maximum possible Q value. And the answer was a lot. So this shows that Q learning without target networks is very unstable, and that a lot of the time you will get this divergence phenomenon. And even as you include tricks that make it progressively more stable, you'll still expect to see divergence every now and then. So we're going to dive into a little bit of math now to kind of get maybe some intuition for why this is the case and what deep Q-learning algorithms are really trying to do and how that translates into the algorithm or doesn't. So we're going to start by taking the operator view of the Bellman equation. So the optimal Bellman operator, T star, is a map from Q functions onto other Q functions. And the value of T star Q for a particular state action pair is given by the Bellman equation that we saw before. The optimal Q function is the fixed point of T star, so Q star equals T star Q star. That's great. And T star has this special thing about it, which is that it's a contraction map on the space of Q functions. Contraction maps have some very special properties that we're going to talk about now. Yay, math. So the main thing about a contraction map is this idea that if you have 2 points and you apply the contraction map to both of them, they'll basically be closer with respect to some distance function after you've applied that map to both of them than they were before. So expressed mathematically, we have some norm, some distance of the norm of a thing minus the other thing. And the norm of f of x minus f of y is going to be less than or equal to some constant factor times the norm of the difference between x and y, that distance between x and y. And when that beta is less than 1, then we have a contraction. That's saying it's getting closer together. It's shrinking. Why do we care about contractions? Because they have unique fixed points, and you can get to them by just repeatedly applying the operator to any initial point. This is something called the Banach fixed point theorem if you're interested in going on Wikipedia and finding something which is going to be more precise than however I've typed this up. But in a nutshell, to show you that they have unique, well, let's forget about uniqueness for a moment, but at the very least that repeatedly applying this operator will get you to a fixed point. If we look at a sequence of points x, and we have a contraction map f with modulus beta, and each point in the sequence is just generated by f of the previous point. And we look at the distance between successive iterates. What we see is that it's shrinking as a function of the iteration number. So in the limit, as the iteration number goes to infinity, that distance will shrink to 0. It will converge. Repeatedly applying it will get you to the fixed point. T star is a contraction on Q functions. So if you could represent the entirety of the Q function, that is to say the Q values for every state action pair in the entirety of the environment, which for all the environments that we care about in deep reinforcement learning, you cannot easily do. You can only do this with function approximation, which is to say you're going to generalize. Whatever you choose for the value in one state action pair will have some influence on another. You can't completely separate them when you do function approximation. But putting that aside, so we could represent all the action values for every state action pair, and we applied T star, the operator, to that function, we would get a new function Q, which is closer to optimal than the one that went in. And if we applied it over and over and over again, we would eventually get to Q star, the fixed point of T star. This is value iteration. It's a classic algorithm in reinforcement learning. So before function approximation, before deep, when you had environments where there were a discrete number of states and a discrete number of actions, and you could represent the Q values in a table of elements, one for each state action pair, you could compute this exactly and use this as a way to get to Q star. Now, when you live in the problems that we do, when you're trying to solve high-dimensional complex video games, high-dimensional complex strategy games, you can't use the table. You have to use a function approximator. And now your problem is that you can't compute all of T star Qi. And even if you could, you probably couldn't find a choice of parameters that would allow you to exactly represent it. So if you want to do this kind of value iteration, you have to do it approximately. And this is roughly what Q-learning algorithms with function approximation try to do, which is that they push the parameters of the network in the direction such that you move Q theta towards T star Q theta. And sometimes this works and sometimes it doesn't, because when you go to this function approximation setting, this operation is not necessarily going to be a contraction on the space of Q functions. You might have lost that property. If you did, expect divergence. In fact, expect things to blow up horribly. If you preserved it or if you've done enough tricks to stabilize it, things will work pretty well. In my experience, Q-learning algorithms and their variants tend to be extremely sample efficient when they work, which is quite desirable. And it's very nice that they can recycle off-policy data, because on-policy methods, sadly, have to throw away tons of it. But last point on Q-learning. What you normally see in deep learning algorithms and deep RL algorithms is that paradigm of there's an objective function and you optimize it and you find the model that optimizes the objective. In Q-learning, don't be misled into believing, however many times you see it, that the mean squared Bellman error is really the thing that you're optimizing. You change that function every time you change the target. The thing that you're really doing is this sort of approximate value iteration. You're trying to apply an approximate operator, which is going to get you to something better. You're not trying to minimize a loss. That's not to say that there aren't variants of these kinds of algorithms that do involve well-defined loss functions. There's a whole family of algorithms called gradient temporal difference methods, which, if you are theoretically inclined and willing to go down a deep, deep, deep rabbit hole, I recommend you check out. Talk to me if you want references. Also, in the Spinning Up Key Papers doc, I believe there's a book in the bonus section for classic RL papers and review papers. Feburary's book on RL algorithms from 2010, which recaps a lot of this really great old stuff, including gradient temporal difference algorithms. So I recommend you check that out if you're interested. Yes?
So how would we, like, are there any techniques to preserve the contraction? Or is it based on everything else?
I'm actually working on some research on that right now. Like, talk to me offline.
Sure.
Yes.
This is the temporal difference for Q and Q prime in the equation. The temporal difference.
Yes. So this thing, yes, is called a temporal difference error because it is the difference in the Q value based on the next time step versus the current time step. Yeah. Yes.
What is the difference between off-policy and when you explain off-policy?
Absolutely. What is the difference between off-policy and on-policy? The on-policy algorithms have updates which are based on the expected values of things, where the distribution in that expectation depends on the current policy. So if you want to form a sample estimate of the thing in the update equation, then you first have to run the current policy, collect interactions with the environment on the current policy, and use those samples for forming that sample estimate. That's on policy, because all the data that you use has to be generated by the policy that you're using at the time. In off-policy methods like Q-learning, what you do when you make an update is you use experience which might have been generated by older policies, not the current one. So the current policy you can think of as being implicitly expressed in the Q function approximator's current value. But many steps ago, it was different, and you got whatever data you got from interacting with the environment. You put that in your replay buffer, and then many steps later, you still sample those states and actions from that replay buffer to help you form your new update to the current Q function. So when the data was generated by a different policy, that's off policy. Yes? In what sort of gaming situation would we maybe use deep Q learning, or like what's a use case for it? So there's a fabulous use case actually. Facebook recently released a paper on their machine learning and RL learning, or their RL platform called Horizon, which they used to train with deep Q learning neural networks for making decisions about when to send you push notifications. So actually DQN is in your phones right now. Okay, then let's proceed to the next part, which is model-based stuff. So I'm going to be pretty brief about model-based stuff. There's a very wide variety of different model-based algorithms, and we're not going to drill down into them the way that we drill down into policy learning and Q learning. But we will give a relatively brief overview of some of the more salient points and a few algorithms that I think are particularly interesting. So back to the loop. Run policy, evaluate policy, improve policy. Where do models fit in? So recall that a model of the environment lets you predict what's going to happen next. You can use that for pretty much any of these. While you're running your policy, before you take an action, you can stop and imagine what's going to happen if you try many different things. You can create partial rollouts that you can use to evaluate your different choices, and then you might pick something different than you would have otherwise. So that's maybe where it can appear in running the policy. In evaluating the policy, you can use that same kind of approach of just simulating look-ahead data to help you get maybe a more stable backup for your queue function. Or just use some kind of Monte Carlo tree search style algorithm where you're going to propagate queue values back and figure out like an average case queue value. And then for improving the policy, you can regress your policy network if you have explicitly represented one towards whatever the outputs were from that look-ahead planning process. So if you have a model, it's very powerful. You can use it in a lot of different ways. You can embed it pretty deeply into RL. The problem is that models are very hard to learn, and you usually don't have them. So let's say you have just made a wonderful, brand new, complex physical robot. Unless you have a lot of hours to spare and control theory expertise, you probably do not know how to fully characterize that and have a simulator model which is going to be accurate in any reasonable way, certainly not accurate enough for training it in simulation and then directly applying that simulation-trained policy into the real world. You may want to try learning a policy from data, but this can be quite tricky, although there are some really exceptional success cases. But because, yes? Yes, you could make that argument. Let's say hardness to learn is not a fun. I suppose. Sorry. The question was, can you make the same argument for value functions? And I would say that hardness to learn in this case should be interpreted more as, has the research community figured out really robust, reliable, standard methods for doing it yet? And not necessarily whether there's some intrinsic quality of hardness. Finding the correct model is a supervised learning problem if you have enough data. Part of the problem in RL is that you usually don't have enough data, and you would have to get it by interacting with the environment, and there may be areas of the environment very critical to decision making which you've just never observed yet. So imagine that you are in a giant maze, and you can try to learn a model of the maze as you go, but until you've seen the exit, your model is not going to be very helpful for you in navigating, except to help you perhaps avoid repeating places that you've been to already. But yeah, in practice, models tend to be, so far, hard to learn. So let's look at maybe one case study in ways that you can use models. So this is the case of planning and or expert iteration. The basic idea is that you're going to use your model from a current state to look ahead into the future and help guide your decision about what action to take. So in planning, you might explicitly just base your decision about what action to take on whatever the output from that look-ahead process is and your current value function. In expert iteration, you're not only going to do that, but then you're also going to have a explicit representation of a policy which you'll try to improve by regressing it towards the output from the look-ahead process. So as a case study, consider AlphaZero. AlphaZero is an algorithm which has succeeded at achieving superhuman performance in a wide variety of complex two-player, fully observed strategy games, particularly chess, Go, and shogi. So this was a successor to AlphaGo, the algorithm that beat human grandmasters in Go. And AlphaZero at the algorithm level is sort of beautifully simple. You have a neural network that emits two things: a probability distribution over moves to play, P, and a value network that says basically whether or not you're going to win or lose, V. And you learn this with this just very simple regression approach where you're going to move the value function to be more like whatever the true outcomes from games were. And you're going to update the policy by using a model-based look-ahead operator to figure out what a better policy would have been based on your current policy and value function. And you're just going to move your current policy towards that. And then there's also some regularization. Very straightforward. And the look-ahead is done with Monte Carlo tree search. So that's just stochastically considering different possible outcomes and then aggregating data after having done partial rollouts down the game tree to figure out what would have been the best thing to do. So this is one model-based approach. Now, this required having a perfect model of the environment. And in games like chess or Go, this is feasible because you can fully express the rules in a way which is easy to compute and forward simulate. And you don't have to learn anything from data. And you also don't have anything which is partially observed. So your model doesn't have to do anything fancy to keep track of what's going on in the background. Very straightforward. And this kind of approach can be very, very powerful. But the problem is that most conditions are not quite as ideal as this. So another family of approaches is where you're going to use the model for policy evaluation. So let's say that you have learned a model, or perhaps you're given one, but more often than not for these algorithms, you're trying to learn it concurrently with experience. You learn some models, and then you're going to have the agent, quote, dream in them. The agent will sample a bunch of fictitious trajectories inside of the simulator and use those as the basis for a policy improvement step. And algorithms that are like this, there's model ensemble TRPO and I want to say meta policy optimization or model-based meta policy optimization. Then you could also, instead of using this for computing advantages and a policy optimization style improvement, you could use this for Q-learning as well, where perhaps instead of forming the target based on the bootstrap, which might be inaccurate on particular regions of state action space that you haven't visited, you could use the model to simulate what the bootstrap might be in those cases and use that as your backup for Q-learning. So that's an approach called model-based value expansion. And these algorithms, the gain that you get from doing this is ultimately in sample efficiency. So what happens in normal deep RL is that you use tons and tons of data from interacting with the environment to try to improve your policy or your Q function. And you make progress at whatever pace. When you use the model and you offload a whole lot of the improvement steps onto experience collected in the model, that frees you up from having to have collected that amount of experience in the real world, as long as your model is good enough. If your model's not good, this won't be very helpful. But if it is good, and if you only needed a little bit of data to train your model, then you can get a lot of mileage out of it, and your overall RL algorithm will have used less interactions with the real environment than otherwise. This is great for cases where interacting with the real environment is very expensive. So, for instance, if you want to train something on a physical robot, that can be an expensive process. The robot might be slow. The robot might break. The robot might have all kinds of things where it's difficult to get it to do that, or it's difficult to reset it. You probably don't want to have to spend that many man-hours waiting around for the robot to finish its learning procedure. So if you can offload some of that time into simulation, then it makes life better. Yes?
Is that what you would apply for self-driving cars?
Is that what you would apply for self-driving cars? That's a good question. So I'm not actually all that familiar with cases where self-driving cars have fruitfully made use of deep RL. That's not to say that they don't. I just don't know. I would imagine that in self-driving cars, it's probably more a matter of collecting data from experienced human experts and then using that data as the basis for learning a behavioral policy. But I'm also happy to, go through this later and see what we can find in the literature. Yes? Would model-based RL be more geared towards transfer learning? I think it could potentially be quite helpful. So certainly, when we think about trying to get robotics to transfer from, say, simulation to reality, we want to make sure that the model used in simulation is high fidelity with respect to reality. And if that's the case, then this model, you can think about sim to real as sort of a model-based approach, and perhaps it's going to be very helpful. All right. And then there's this other completely orthogonal way of using models, which I'm really fond of because it's just sort of weird, which is that you actually take the model and embed it inside of a model-free agent, where the model is going to receive inputs from the environment and use that with some internal process of perhaps imagining some futures and then transforming whatever representation it has of those futures into something which then becomes side information to the model-free agent. So you train the model separately from the agent. The module that provides some information based on the model to the agent is sort of decoupled from it, except that however the model-free agent will process that information is based purely on the model-free learning. So this is an approach called imagination augmented agents. I think this is really interesting and really neat. I'm not aware of a whole lot of follow-up work from when this came out, I want to say last year or the year before, but I just think that because it is so different from the other model-based approaches, that's cool. Whenever there's something different, it's cool. All right, that takes me to what was originally intended to be the end of part one, but is now the end of both parts. Thank you so much. At this point, I would like to turn over the mic and the stage to Matthias Plappert, who is a researcher on the robotics team at OpenAI, and he'll be presenting on the work on the robotics team for learning how to do complex manipulation with deep reinforcement learning on a real physical robot.
Great, thank you. Do we have a computer? Sweet. Yay, I think it works. Okay, thank you. Cool. So hey everybody, my name is Matthias, as Josh mentioned. I'm super excited to be here and talk a little bit about what robotics at OpenAI is doing. And the talk that I'm going to present is called Learning Dexterity. As I mentioned, this is basically the effort of the entire robotics teams for many months. So everything I'm kind of talking about is not just my work, but the entire robotics team's work. Cool. So let's maybe start with talking a little bit about what robotics at OpenAI is actually trying to do. And the ultimate goal, I guess, that robotics at OpenAI has is to build some form of general purpose robot. So I think this kind of picture illustrates this very well. We have human-like robots today, and we know that humans can do a very, very large amount of different jobs and skills. So that can include things like cooking, it can include things like actual labor in some form of agricultural thing. Maybe it's very precise kind of things like surgery or building things and putting things together and this kind of stuff. And ideally, we would like to have a robot that has a similar level of dexterity and a similar level of, well, general purposeness, if you will. The way robotics looks right now is very different from that. So we have these kind of very specialized robots. So an example I think that is good is the Roomba, which is on the lower, in the upper left corner here, that can clean your house, but it can only clean your house. It can only vacuum your house. And similarly, you have things like self-driving cars, which to some extent are also robots that are very good at one thing, which is driving themselves, but they cannot do anything else. And the robots that are more kind of versatile and more complicated, they are either very often controlled by humans. So an example for that would be doing surgery. So we have robots that can assist humans in that, but they're always controlled by a human operator, which is a surgeon. Or we have more complicated robots in factories, but those are typically just programmed to basically blindly execute a given trajectory. So someone sits with the robot and figures out how to do a certain process in a factory, and the robot is very, very stupid and has no idea what's going on. So the question, of course, is how can we kind of step away from that paradigm, and how can we have robots that work in the actual physical world and are aware of their surroundings? And given that this is the spinning up workshop that's concerned with RL, it's not too surprising that we think RL may be a good approach to that. And we know that RL works really well in certain domains. So I've picked out 2 examples here that probably most people have seen. On the left side, we have AlphaGo Zero playing against Lee Sedol, a game of Go. And as you know, AlphaGo Zero won this game. In fact, I think it won almost all games that it has ever played. And the follow-up versions of AlphaGo Zero are beyond human capabilities when it comes to playing Go. Similarly, we have Dota 2. So this is some of the work that the Dota team at OpenAI has been doing for a while. We have this Dota bot called OpenAI 5 that is very, very good at playing the game Dota 2, which is a 5v5 multiplayer game. And it is approaching like professional levels. So it's consistently winning against semi-pros, and we are already playing against some pros. In fact, we have done that last summer at the International. Unfortunately, we have not yet won against those pros. So the question is, how does this work in robotics? And of course, there's like a lot of work in this in robotics. It's not like we're the only ones doing this. And I'd just like to give a bunch of examples that I think are kind of illustrating what people are typically doing today. The first approach here is somewhat recent. It's from 2017, and I think it looks really cool. So you can see the agent is even able to use certain tools. So in this case, a hammer. It can open doors, it can do all sorts of things. The unfortunate thing here is that all of this looks really cool, but it's only in simulation. And ultimately in robotics, it doesn't really count if it's only in simulation because you want the physical robot to do something. Otherwise, it's not very useful. So the other approach that people have been taking is to train on the actual robot itself. So this is some work from 2016 where people have been doing dexterous in-hand manipulation. So the goal of the robot here is to kind of manipulate this tube filled with coffee beans for some reason into a target orientation. And they do all the learning on the actual robot, and that of course has the advantage of not having to do any form of transfer. Because you learn on the robot, you exactly know how the robot is going to work, and once you have a good policy, you're done. The downside of that, of course, is that, well, you have to run on the actual robot, so it kind of breaks a lot on you. It's very slow to do. You can't really scale this up unless you get a lot of robots, which is actually something that people are doing. So this is the approach taken by Google. In typical Google fashion, scale it up. So just get a lot of robots and let them do it for 2 months in parallel. And then you can suddenly train on the robot because, well, you have 20 of those doing it in parallel, and it can do very meaningful stuff. So in this case, they have learned to grasp arbitrary objects out of this kind of box that they have sitting here. And this is actually a very impressive demo. Like this kind of bin picking stuff is actually very hard. The thing is still that obviously this does not really scale all that well because this is a relatively simple task, yet you need 20 robots going for 2 months. And you will also just have to babysit the robot all the time, right? Like you'll have to repair it when it breaks. You'll have to kind of reset the environment when certain objects fall out of the bin and all of this kind of stuff. So it's just a lot of work. So what we're trying to do is to kind of combine the benefits of those 2 approaches. So training and simulation and then transferring to the physical world, which is called Sim2Real. And I'll be talking a lot more about this. But before I do that, I'd like to introduce you to the task that we actually have in mind when we do our research. So we decided to do dexterous in-hand manipulation. And the reason for that is that it is, first of all, very hard to do. And then second of all, it is something that we're interested in because we know that our hands are these universal end effectors, right? So human hands are very versatile in what they can do. They can be very dexterous. You can do a cooking thing, or you can operate on a human if you're a surgeon at least. But you can also do very heavy lifting with it, and you can use tools that are made for humans' hands and these kind of things. So this is basically the motivation for why we choose this kind of hand and this kind of task. Because it's hard, and because it's also ultimately useful for the general purpose robot we would like to build. And the reason why it's hard, I think, is summarized relatively well in this kind of slide. So we use a hand called the shadow dexterous hand, which is depicted in this picture. It has 24 joints, and it has 20 actuators. So what this means is that your policy in every time set has to produce an action for 20 individual actuators, and it actually has to coordinate them, right? Like you'll have to have different joints work together to do certain things. So it's a really high dimensional kind of control problem that's typically well out of reach of what traditional control problems can solve. As I mentioned, ultimately we want to run this on real hardware, and so we have to work with the real hardware and all its flaws and issues. So this includes things like noisy and delayed sensing. So that's just a fact of physical hardware systems, right? Like they will not have perfect information, and they will have delays and certain quirks that you kind of have to deal with. The other issue that comes out of this sensing is that you actually have to handle partial observability. So in simulation, you have perfect knowledge of everything that's going on because, well, it's your simulation, and you can just read out from your simulation what the current state is. But on the physical system, you can only use what you can actually sense. So obviously, certain things like the friction, for instance, of the system cannot directly be observed. And then last of all, this is actually super hard to simulate, as it turns out. The reason for that is that you have a lot of contacts going on. So if you have something in your hand, like you kind of constantly touch it, and contacts are notoriously hard to model accurately, first of all. And then the hand itself is also incredibly complicated. So it's tendon actuated, which means that you kind of have tendons pulling, and this causes a lot of unmodeled kind of things in your hardware that you have not modeled in simulation. Cool. So as I mentioned, we set out to solve this problem with our sim-to-real approach. So we train in simulation, and then we transfer to the physical hardware. And while this sounds very easy, it is not very easy. Because the transfer problem, as you'll see, is actually not very easy to overcome. But before we talk about that, let's have a look at what we can do in simulation and what the policy that we train looks like in simulation. I think this also illustrates the task at hand so that you can actually understand later what the robot is trying to do. So as you can see, you kind of have this block with colored faces, and the task is to rotate this block into the desired target orientation that you have. And the target is depicted as this kind of like semi-transparent additional block on the right-hand side. So now it's trying to bring up the blue face A. Yeah, it got it, and then it kind of moves on to the next goal. And as you can see, this kind of involves like it coordinating its fingers. It has to kind of use its palm. It's kind of using gravity to let it roll. And it's like even in simulation, this is not super easy to learn. The hardware itself looks like this. So this is the cage, we call it. It houses all sorts of things. In the middle, of course, you have the shadow dexterous hand, which is the robot itself. And then you have it surrounded by quite a lot of these face-based tracking cameras. So we have 12 of those in total. And what they do is they provide you with relatively accurate sensing in Cartesian space. So we have LED markers on the hand itself, so we know where the hand is. And we also have LED markers on the object, so we know where the object is. And those guys, basically, they sense the light of the LED, and since multiple cameras can kind of see the same LED marker, they can do triangulation, and you can recover the position in space from that information. We also have an alternative setup because, as I mentioned, ultimately we'd like to have something that's more general, and having a motion capture system is not very kind of real world like. So we also have RGB cameras. So those are regular RGB cameras. We have 3 of them surrounding the scene, and they can also be used for sensing. In fact, they can be used for pose estimation of the object, so you don't even have to have any special kind of sensing on the object itself. The cameras can do it for you. And the reason why we have 3 is just so they can first kind of recover depth information, and then second, they can also kind of work around occlusions because it's in the hand. From certain angles, you kind of sometimes see the object because it's kind of covered by the hand. So this is how it looks up close when we run things. So as you can see, we have the hand with the block in its palm. And in this case, it's the block that we use for face-based tracking. So you can kind of also see the LEDs on it that we use. This is simply much easier to do when kind of testing these algorithms. So we have these kind of dual setups. All right. So the big question, of course, is how do we do the transfer? So I showed you a video of the policy doing its thing in simulation, and I showed you the physical hardware, so we kind of have all the building blocks. But how can we actually transfer it to the physical robot? And if you just train it in simulation, it will not work at all. It's the short version. So I'll be showing some kind of numbers for that as well. But there, you can believe me if I say the transfer problem is really the core issue that we're dealing with here. And the approach that we're taking is relatively straightforward, actually. So what we do is we use two main techniques. The first one, of course, being reinforcement learning to learn the actual control policy. And then the second technique being domain randomization to make sure that the learned control policy actually transfers to the physical system. And I'll be speaking about both of those in a little bit more detail. So let's get started with domain randomization. So this is a technique that has been used for a little while. A pretty popular paper when it comes to this is from 2016. In this paper, what they did is they learned to fly a drone. And the way they approached this is they trained it only in simulation using these kind of randomized buildings. So you can kind of see it has a lot of different rooms in it. The textures are very different, so the walls look different, the ceilings, the floors, and they train a drone to fly in all of those rooms. And what they then do is they take this drone that was only ever flying inside a simulation and show that it can actually fly in a completely different actual room. Simply because it kind of has seen all of this variant during its training, it kind of, like from its perspective, what happens is that the policy thinks, oh, just this is another like randomization, it's kind of weird, but oh well, I know how to handle it. So it flies in the actual room. And people at OpenAI have been using similar approaches as well. So this is some work from my colleague Josh Tobin. What he has been doing is he has been using domain randomization for grasping. So this is using a robot called the Fetch. So it's you'll see a better picture in a moment, but it's basically a simple robot arm with a parallel gripper at the end. And what he would like to do is pick up these objects that you kind of see in these randomized scenes. And by basically using the same approach, so he's randomizing all sorts of things like the looks of the objects, the shape of the object, the background, the color of the table, as you can see. He can then use this information or this training to transfer to the physical robot, even though it has never seen the actual physical table. And what was pretty surprising in this research is that it turns out you don't even need photorealistic rendering. So as you can see, like this looks not realistic at all. It's like pretty shitty computer graphics. And still it transfers to the physical world. So the important thing here is that you have this variety and not necessarily realistic environments. Yeah. Yes, so all of the two approaches that I showed are using vision to learn a policy, yes. In this case, I think it's actually not using the vision to learn a policy directly. I think it's instead just predicting the location of the object, and then there's a policy that kind of can grasp it from that. So some other work in this domain, which I think is equally important, is physics randomization. And this has been done by Jason Pang, who used to be an intern at OpenAI in 2017. And he's basically using the same idea of randomizing, but now for physics instead of like visual appearances. So it's kind of hard to like visualize what's going on, but what the policy in training sees is certain worlds that are just different. So maybe they have different masses, maybe they have different frictions of the table, maybe the robot itself behaves differently, and so on and so forth. And what he was able to show is that this, again, is sufficient to train strictly in simulation and then transfer to the physical robot. So the task at hand here is, again, with the Fetch robot, and it's trying to move this puck to the goal location, which is marked in red. And on the left-hand side, you see a policy that has been trained with this physics randomizations. On the right-hand side, it has been trained without. And as you can see, obviously, the one on the left-hand side does a pretty decent job. It's like relatively precise. It can push the puck where it wants to go. And the one on the right kind of freaks out. So it shakes very violently. In fact, the building was shaking when he was deploying this. And it cannot really do the job. And the reason is that it, well, has kind of overfit to the simulation, which simply is not fully accurate, even though it's calibrated to be close to the robot. And then it doesn't generalize to the actual physical world, whereas the one with physics randomizations does. Okay, cool. So that's domain randomization in a nutshell. So both the visual randomization and the physics randomization. Yeah.
Was the physics randomization realistic, or does the same rule hold as for the visual one, that it doesn't matter?
Yeah, it's not very realistic, honestly. I mean, it's realistic in the sense that it's still physical. So if you randomize too much, your simulation will become unstable because you've set certain parameters such that they cannot make sense anymore. But it's not very realistic. Like the masses will be very high sometimes. It's like super hard to move the puck, and it's more about diversity again. Yeah. Okay, cool. So I'll now speak about our approach. So what I previously talked about was mostly other people's work, even though they're also on the robotics team. But this is the learning dexterity approach that we took. So again, remember the goal is to have the shadow hand rotate an object in hand. And to kind of start us off, I think it makes sense to just give you the overview of the entire system end to end, and then we'll kind of dive into some of the details after that. So again, as I mentioned, everything we do is only in simulation. So we never see the actual physical robot until we run on it. Like we've never seen it. So the way it works is that we collect a lot of data in simulation. So we have many simulations running in parallel, which is kind of depicted here in box A. And all of those are randomized, which is kind of visualized by them having different visual appearances, but also think physics randomizations. So the friction and the masses will also be randomized. And using this collected data, we basically end up training two different networks. So one of them is a policy, and the other one is a vision network, because we'd ultimately like to run this from vision alone without the face space. The policy network is what is depicted in box B here, and the way it works is that it takes the observed robot state, which is the position of the 5 fingertips, so you have those in Cartesian space, so 15 dimensions in total, so it knows where its fingertips are, and then also the pose of the object, so that means just the orientation and the rotation in space, sorry, the position and the rotation in space. And this information is then fed into an LSTM policy, so it's a recurrent policy, and it produces the next action, and we train this in simulation using reinforcement learning. The second network that we have, which is actually distinct, they are not end-to-end, this is two networks that we train separately, is the vision network. And the way the vision network works is that it takes 3 different images, so remember we had these 3 RGB cameras surrounding, so images rendered from the perspective of those, but again only in simulation, and then using a convolutional neural network predicts the pose of the object from that information, from those images. And again, this is only trained in simulation. When it comes to actually deploying this to transfer, as you can maybe kind of guess, is that we can combine those two systems to get us what we ultimately would like. So you use the actual cameras to sense the position or the pose of the object using the vision network, so you feed it into that. And then by having the object pose and the fingertip locations, you use your LSTM policy to produce actions. And that allows the robot to basically see what is going on and react accordingly while only being trained in simulation. Yeah.
The object pose estimation using CNN better than traditional techniques, like vision?
Potentially. Honestly, we have mostly used this approach because we knew it worked from previous research. It is almost as accurate as face-based, and face-based is very accurate. I think if you spend a lot of time, you could probably develop something with more traditional methods. I don't question it, but like we would like to have something that's more general again. And having a convolution neural network do it seemed like the most general approach we could have. Yeah. Yeah, it's kind of interesting. So ideally, you would just use whatever the robot has as joint sensing. So it knows, or it should know, what its own joints are. As it turns out, the sensing in the shadow hand uses Hall effect sensing, which is a magnetic kind of sensor, and they interfere quite a lot. So if your fingers are close together, you will actually not know where your fingers are. So that's the reason why we don't use it. We would like to use it, but it turned out to be not precise enough for what we ultimately wanted to do, so we couldn't actually rely on that. But yeah, you're right. Like this is more of a workaround. Like ideally, the robot should just tell us what the joint positions are, and then we wouldn't need the fingertip positions. No, it actually has very limited information. It's very surprising that it works like that. Yeah. Yes. Yeah. Yeah, very good question. There's a lot of debate about this. I don't think it does. We have some indication that it doesn't. In fact, it seems to help. Like the performance seems to improve over the board. Like we have certain ways of measuring sim-to-sim transfer, and when we randomize more, we tend to get better performance on all the environments. So I don't think it's compromising actually. I think it's more of an adaptive policy. But then there's people who disagree. So it's currently a little bit unclear. Okay, cool. So as I mentioned, we need to randomize. And of course, we use appearance randomization. So this is only for the vision network. So this is basically what I just described before, just for our setup. So you can kind of see we have the 3 different cameras showing the same scene, and we randomize the scene quite heavily. So the robot changes its color, the background changes its color. Importantly, the block itself stays mostly the same because it actually has that color. Like you cannot randomize it arbitrarily. But we changed like the material of the block as well, so it looks slightly different. And then we of course have the vision network, which again is relatively straightforward. So the way it works is it takes those 3 camera images, then uses convolutions and the ResNet architecture and spatial softmax to kind of process them, and then simply concatenates all the things and produces the final object position and object rotation, so the pose of the object. And this is simply trained with supervised learning because in simulation, you actually have perfect ground truth, which is another very convenient thing. You actually perfectly precisely know where your object is. You have not to actually sense it at all. And this is what the model actually sees. So it's actually, I think, very interesting because it looks very, very different from the randomizations. And yet it generalizes to that simply because it has seen enough variety that it's kind of okay with yet another variety that's kind of weird, but still within distribution in that sense. So when it comes to the physics randomizations that we use, we randomize quite a lot of things as well. So we have things like object dimensions, for instance. We have things like masses, obviously, and then mostly things about the robot itself. So things like the way we actuate the robot, things like damping within its joints and all of this stuff. And the reason for that is that it's actually very hard to measure this. So another neat thing is that you can, in this physics randomization, actually account for your uncertainty. So for the object dimensions, we know those with relatively little uncertainty because we can just measure the dimension of the block. But things like the actuation we know much less about, and so we kind of widen the randomizations for those. And another kind of cool thing is that we randomize the gravity vector, which may seem a little bit weird, but it basically amounts to, like, when you mount the hand, it's not perfectly parallel to the floor. Like it will be slightly angled because of imperfections. And by randomizing the gravity vector, you kind of get this effect as well. Like it's sometimes slightly angled, and it turned out to be actually very useful. And then we of course also have noisy observations and noisy actions, simply because it's a reality of the physical system. The policy is very, very simple. So what it gets is the noisy observations. So that's the 5 fingertip positions and the pose of the object, and the goal. So it knows what it wants to do. And then we normalize a little bit. So this is just making sure that things have 0 mean and unit variance. And then use one fully connected ReLU layer and one LSTM to produce the action distribution. And from that we sample and then perform that on the robot. So it's a relatively shallow and relatively small network overall. The more, oh sorry, yeah. They only come in through the simulation. They cannot be observed directly. So, sorry?
Position of the fingertips, yes, they are in the observation,
Mm-hmm.
and the joint angles are in the action. But all the intermediate parameters that you mentioned, where are they?
They are simply set in the simulation. So the environment has been changed, but the policy cannot sense this directly. It has to infer this basically, because on the physical robot it also cannot sense it. Like we don't know what it is on the physical system. So it basically, what we think it ultimately ends up doing is some form of system identification. So when it's running, it's implicitly inferring certain information about the environment and then using this information to kind of adapt itself accordingly. Yeah? Sorry, I couldn't hear.
Do you inject high frequency noise like white noise?
Yeah, so we add Gaussian noise to the observations and to the actions. Yeah. All right. So I think I'm running a little bit late, actually. How bad is this? Huh? Okay, then we have to hurry a little bit. Cool. So distributed training. Let me speak about this, and then I'll show a video. So distributed training, I think, is very interesting because we use basically the same system that the Dota team uses as well. So we have a very large-scale kind of system, and the way it works is that we have roller workers who generate a lot of experience, and then we have an optimizer machine that's kind of using this information to update its policy. And we use proximal policy optimization for that, so an on-policy algorithm, as I think Josh has explained earlier today. And I think it's kind of cool that we use the same system as Dota. Let me skip over some things, but I think I want to show this. So this is when it's running on the physical robot. As you can see, it's using vision, so there are no markers on the actual object. The robot hand is doing all of this. This is not cut in any way, it is not sped up. Again, the goal is depicted in the right corner here, so it will try to get the E face front and the N face up top. And it will get to 50 successful rotations in this case. So it can do quite a lot of those, and it can run on the physical system. And if I have enough time, one kind of final thing that I think is actually very interesting is that it actually learns certain strategies that happen to have names. So we have finger pivoting, where you kind of like use your two fingers to create a rotational axis, and then you rotate around that, and things like finger gating. And the reason why they have names is because they are used by humans as well, and they have been kind of studied very well. They emerge automatically in our case. So we have never shown the robot what a human would do. It has kind of discovered that itself. And the reason why they come up is simply because it has a human-like morphology, right? Like it has a human-like hand, and it just turns out that these strategies are equally useful for humans and robots, but they have kind of been rediscovered, quote unquote, which I think is a really cool thing. So I wanted to mention that. And yeah, we have some quantitative results that show that randomizations are very important. So if you don't randomize, you get no successes. If you randomize, you do. It turns out memory is very important, so you need an LSTM. You cannot simply have a feed-forward policy. And you need a lot of experience. So for the final policy, we used 100 years worth of data. So imagine doing that on the physical robot, like probably not such a good idea. But we can get away with it because we use simulation. So we do all of this in 50 hours. And I think with that, I have to close. All right, thank you.
That was great. Thank you so much, Matthias. We're going to switch out the slides, and then please welcome to the stage the leader of the safety team at OpenAI, Dario Amodei.
All right, just a minute to get the slides.
It's a very good thing that you're ensuring that computers in the future will not be as malicious.
I have often joked that solving general intelligence will be easier than solving video conferencing. I think it might be true.
Unfortunately. Okay. This is yours. And give me a second.
Cool. So I work on a team at OpenAI that thinks about making AI systems do what humans want them to do, which is, kind of very central to OpenAI's mission, and which we think of as something that our focus on distinguishes us from other organizations. We think it's very important, particularly as systems get more capable, to ensure that they, both in a narrow and broad sense, benefit society. So this workshop is called Spinning Up in Deep RL. So it's useful to step back and think about what is RL accomplished in the last couple years and where is it going. This is actually out of date. We should add a couple things to it. But if we look at playing games like Go, if we look at from about a year ago, multi-agent behaviors where you can use RL and self-play to train agents to sumo wrestle each other off a pad. We are able to play competitively against professional players in Dota 2. The robot results, which you just saw, and we should probably add just in the last week or two, the results we've seen on StarCraft, which is in some ways similar to Dota, but just a different kind of game with a different kind of properties, and yet that shows that these techniques are really pretty general and are advancing pretty quickly. If we step back and reflect on kind of where are things going, some properties that we could point out of these RL agents that are becoming more and more true, right? That were not true 5 years ago, but are becoming more and more true. We have systems that have an extended interaction with a complex real-time environment. They have a very high level of autonomy and speed. You can imagine systems like this in the real world being used to make decisions faster than humans can intervene, or in more complex ways than humans could hope to understand. So, regulating the economy or financial system, managing large networks of computers, these are the kinds of things that as RL technology matures, it will be better and better able to do. And these systems, unlike supervised learning systems, and unlike in any interesting way, the simple RL systems of a few years ago, these systems are able to teach themselves and discover their own strategies. And in many cases, they discover non-trivial strategies. Just like we saw with the robot, it kind of recapitulating a lot of strategies that humans use. We see in Go and Dota and StarCraft a lot of human strategies that have names. The RL system discovers and recapitulates, but it also sometimes discovers strategies that a human would never have thought of. So if we look at what these properties mean together, one thing it means is that the connection between us as designers specifying what we want the system to do and what the system actually does. In theory, if everything is done right, the system does what we want. But that rope, it's longer, it's more frayed, it's more tenuous than for just kind of less autonomous systems that we've designed in the past. And there are many ways relative to simple computer systems or machine learning systems like supervised learning for these systems to go wrong. And so a couple years ago, several people, on most of whom are now constitute the OpenAI safety team, started thinking about this. We're worried about current systems, we're worried about tomorrow's systems. Eventually, we're worried about about building general intelligence and what that will mean for the world, and making sure that those systems are safe. We wrote kind of a position paper, and this kind of started us thinking about the directions and how to even think about this problem of do systems reliably do what we want them to do. And the kind of general framework and division we came up with was, okay, so let's narrowly scope the problem. We're speaking not about kind of wider societal impacts, although those are also important, but just narrowly, the designer had a clear thing they wanted the system to do, and then the system gets trained, it gets deployed, it goes through some long process. Actual system fails at this catastrophically. And we kind of divided it up into a couple things. One is, you're giving the system some direction, some objective function that it learns from, like the reward in RL. There are ways for that to be subtly wrong, and you can get spectacularly wrong behavior if that happens. You might have the right objective function, but your system has problems with robustness. Doesn't generalize well. It exhibits unpredictable behavior. As it's learning, it does dangerous things, even if the final policy it's going to learn makes sense. And then as a reminder that there are like this all exists on top of kind of software implementation that has bugs in and of itself, and so the A and B are new, but they're layered on top of the general unreliability of software. So kind of a useful way to think about, let's put C aside because it's not really a machine learning problem, more just a reminder that this is layered on top of existing problems. But a crude analogy we can make is, it's a bit like the simple statistical concepts of bias and variance, right? Better objective function, that's about reducing bias and making sure you're aimed for the right target. Robustness is about making sure that you're narrowly clustered around the target and that you always get what you're intending to get. So we're interested in both problems. Because I have limited time, I'm going to talk about our work on the getting the objective function side right. I think OpenAI does more. The OpenAI safety team does more of that relative to other teams, say at Google Brain or DeepMind, that think about these problems. And so I'll mostly talk about that, but increasingly, and maybe I'll have a little bit of time to talk about it at the end, we're also thinking about the robustness direction and how these two things interact. So just to be clear about what we mean, I think this video has been widely circulated, so I apologize if for people who are already familiar with it. But about a year and a half ago, we were training lots of Flash games using RL, and there happens to be this boat race game. So I just set lots of games running with a reward function. So the way this boat race works is you're supposed to go along a course, and you're supposed to finish the course. But the way the reward function works, and it's hard to reach in and write a different reward function, is you get points for these markers along the way that are mostly along the course. But it turns out there's this little lagoon in the corner of the course where you can go around in circles and get more and more power-ups. And that turns out to get you a faster rate of power-ups than actually finishing the course. There's nothing wrong with RL here. The system did what it was supposed to do, but it identifies the weakness of the connection between a reward function and the final behavior. The reward function that you specify, that you may think corresponds to some behavior that you want, may in fact correspond to very different behaviors. And you get no feedback on that other than just finding out what the system does, right? When I first trained this, I trained it along with a bunch of other games. 2 days later, I looked at this. I'm like, what in the world is this doing? It doesn't make any sense. And then I thought about it a lot. I'm like, oh, of course that makes sense. So the more powerful the system is, the more autonomous it is, the less a human is paying attention to it, the more potential there is. This is like, I can generate dozens of these examples, but a robotic system where we forgot to make the table totally fixed. It has a high mass, but it's not fixed. Turns out to be easy. It's hard to send the puck exactly to the point you want it to be. It's easier to send the puck, observe if it's going to be a little to the right or a little to the left, and then nudge the table so that it hits it exactly. It's very clever. It's a correct solution to the problem, but the problem was not the right problem. The general approach that we've kind of hit on, and we've been pursuing this strategy for about a year and a half, is that this training loop is too long, right? The human at the beginning says, here's a mathematical reward function, like go optimize this. Then you look back at the end of training, you might get the right thing, you might not. If you don't, you have to go back to the beginning, or maybe the system's already doing something dangerous. So maybe we should have humans be involved interactively in the training process, right? When we train humans to do things, it's not just like, here's your goal, go off, tell me what you did, 2 weeks later. So if we do this, is there a way that we can use a human to decide what the reward function is in a continuous way that's more reliable, that's more naturalistic, so that the system ends up imbued with human goals and values, but it's able to act faster and bigger than human scale. Once it's trained, it knows what the human wants and it does it. Example of this is like instead of RL, we can learn from demonstrations, but that kind of has the same problem. A human demonstrates it, AI system copies it, and there's it's hard to do better than the human, it's hard to course correct, it's hard for the human to say you should be doing this instead of this, and traditional RL has a loop that's too long. So the kind of first effort we did in this direction was, we called it Deep RL from Human Preferences. So the idea is, I want this thing to do a backflip, and it's it's hard to mathematically specify the reward function for a backflip. We tried by looking at all the individual joint angles, and it turns out it just gives you something very, very very awkward looking. But what we do instead is, and this is now running for the second time, but a human looks at the behavior of the system and says, which of these is more like a backflip than the other? The system just starts by acting randomly. It has just like a random reward function. And human gives it feedback on what is more like what the human wants. And then the AI system, like the RL system has a reward predictor, and it tries to fit a reward predictor consistent with what the human says the human prefers. And then in the background, it's running a whole bunch of copies of the RL environment, and those copies optimize the reward function that it learns from the human. The human only ever has to give feedback on a very small fraction of the AI system's behavior. It doesn't have to see everything it does, just has to get enough samples to give the policy an idea of what the reward function should be. So another way to put it is the human trains the reward function, and the reward function trains the RL system. What I just said can be kind of pictured in this. The gray part is the standard setup for reinforcement learning, where you have an RL algorithm in the environment, they exchange observations and actions, and there's a reward that comes from the ether that was ultimately specified by a designer, but that isn't thought about as being part of the problem. Here, what we have is that reward starts out being completely random, and the human sees examples of the agent's behavior and feeds them to a reward predictor. So the reward predictor is changing and improving and adapting over time, and the RL system is both learning from the existing reward function and adapting to changes in the reward function.
Just curious, are you curating which examples you're showing the human to get maximum information, or is it just random?
So we did several versions of it in our paper, and we found that a simple active learning technique helped relative to random. It didn't help by that much, but it helped. The idea is you train an ensemble of reward predictors that are trained on subsets of the data, and that allows you to have kind of like semi-independent predictors. And you can pick examples where the predictors are uncertain, meaning that those are parts of the space or situations where there's just the reward predictor has more uncertainty and so would like more feedback from the human. That helps. You can go much more sophisticated in that direction, right? The system could like ask the human like what am I doing that's wrong? What am I doing that's not clear? The human could say to the system like, I'd like you to produce some examples of this, right? And then it becomes much more like a teacher to human pupil teaching process. And a lot of what we're doing is kind of going in that direction, but we kind of have to start. So imitation learning has the following limitations. When you do imitation learning, except for noise reduction, which is usually a small effect, you can't perform better than the human does. So as we'll see in some future tasks here, there are cases where learning from preferences allows you to perform better than how the human does. The reason for that is with imitation learning, you just do what the human does. Here, you learn what the human wants. And once you learn the reward function, you could do it better than the human, right? So consider something like, if I didn't know how to play Go, I can teach you the rules of Go, and then you can do RL on the rules of Go and get much better than me. Or you can just copy my moves. If you're just copying my moves, you can never do better than me. If I teach you the rules and then you use RL to learn how to play, you can then. Oh, that wasn't good. You can then, in principle, do better. Another difference is you tend to get kind of like better sample. You tend to get like better sample efficiency. You can come up with strategies that a human wouldn't. You can come up with strategies that a human wouldn't have thought of, and many tasks a human just can't do. So actually, this backflip task, it's actually very hard for a human to demonstrate that task. Like you'd have to get a VR set up. And if we look at like the tasks of the future, right, where, like let's say I want to defend, a large corporate IT network or something, and I want to respond to threats in real time. That's just something where I can't get training data from a human. I'm asking the machine to do things that a human can't do, which is what we ultimately want AI systems to be able to do. Does that kind of answer the question?
Yeah. Another one is what if the human either doesn't know, like the preference is kind of like the human maybe doesn't know intentionally or unintentionally?
Yeah. So we have an option in this paper for basically I don't know, or I think we had separate options for I don't know, where it just throws out the data, or these two look about the same, in which case it like weights them equally in the predictor. So that's easy to incorporate. I think ultimately the communication needs to be in terms of language and not in terms of clicking left or right, and then that will kind of like make a richer space for doing things, and saying I don't know, or like show me some other examples, these things aren't comparable at all, will then become much more common. So the nice thing about this is, given an environment, without changing the code at all, only changing what the human provides as feedback, you can get totally different behaviors. So in about half an hour, a human can train this RL system. This is like simple Atari Enduro game. I can train it to do the usual thing, which is to race ahead of all the other cars. But I can also train it to go exactly at the same speed as other cars. And when it does that, it's able to actually get very effectively, like, stay exactly even with other cars, which isn't easy. You have to go at kind of exactly the same speed and match their speed. And so exact same code, just the human provided different feedback. One thing we show is if we don't give you the rewards for Atari games, we just hide them from you. Humans giving feedback on basically, trying to get the system to get the highest score that it can works really well. On the kind of right of each panel, those like colored bars that are moving, that represents how much reward the system thinks it's getting, or just how much it thinks a given action is good. So if you look at the breakout case, when the ball hits the paddle, instead of on the left, when the ball hits the paddle, instead of instead of the ball going to the bottom, it says, yeah, I got a lot of reward from that. Same with Pong. When it surfaces to get oxygen in Sequest, it's very high reward level. So the predictors seem to correspond to what human would say is good behavior, which is not surprising because a human trained them. We did a bunch of experiments, and with fixed reward Atari games, your goal is just to do as good as you would if you knew the reward, right? So you're like hiding the reward from yourself, and you're trying to learn the reward from a human. So most of the time it does almost as good, but actually there are cases where it can do better, where in Enduro, the algorithm we used, A3C, has trouble learning Enduro because of sparsity of the reward. But a human actually helps to shape the reward, right? In Enduro, you have to kind of rev the control stick to go at a certain speed in order to get any reward at all. So you can start to move, and the RL system doesn't give you any reward, and then you have to keep moving faster and faster to get reward. And some algorithms never figure that out. But the human will basically say, okay, yeah, you went ahead, you made progress. That's better than when you're not moving. And so little by little, with a few feedback points, it can lead the system. And so the human can shape the reward. And there are actually cases like the curve for Enduro in the bottom right, where you can actually do better than the human did, or you can actually do better than a standard RL algorithm did, even though you had less information. Instead of knowing the right reward function, you just had a human indicate the reward function. Also works for a bunch of simulated robotics tasks. We haven't really tried it in the real world. Relevant to the question about demonstrations, we actually followed this up with an effort combining human feedback with demonstrations. So what that did is, there's some task, human can do it, but we'd like the RL system to do it better. However, we can initialize from human demonstrations. The AI system copies that, but then on top of that initialization, we run RL with human preferences. So there's no reward function. There's no programmatic reward function anywhere. It's entirely learning from humans. But the first step, the human demonstrates, and then the second step, the AI system copies and the human says, it would be better if you could do it this way. And again, the second step allows you to exceed human performance or do tasks that humans can't do, right? The human's like, this is as well as I know how to do it. The AI system copies that. The human says, okay, well, I wouldn't be able to do this myself, but if you moved back and forth really quickly and shot those two ships, that would be better than if you didn't do that. The AI system is capable of that, and so it can bootstrap itself to kind of beyond human capabilities. More recently, and we don't have any work out on this, but I think we will soon, we started applying this to natural language. So in the last year or so, there have been kind of a lot of progress on large language models like OpenAI's GPT and Google's BERT, where you just take a big corpus of text, you train just a big transformer model to predict the next word or the next token, and that allows you to generate very coherent text and can also be fine-tuned to solve a lot of linguistic tasks. So one idea there is, can we fine-tune that via RL from human preferences, right? I have a language model. It's seen a lot of text. Some of it's happy, some of it's sad. 5 minutes? Some of it's formal statements or informal statements, some of it's jokes. The language model maybe has some idea in its internal representation of the difference between those things. But if I just sample from the language model, it just kind of gives me random samples of stuff. So can I push this language model in directions and to produce behaviors that only a human can specify, that can't be specified programmatically? So things like statements that rhyme or statements that are in iambic pentameter. Could you make a system that is, from the logic of learning from human preferences, is a better poet than any human could be, or something like this, or makes like very positive sentiment statements that are, that it's hard to find enough positive sentiment statements to copy from. So that's the direction we're going in, and then I think like a long-term vision for it would be, we want a system that basically has an ongoing dialogue with a human. The human asks it to do something really complicated, like planning and executing a mission to Mars. The system kind of clarifies, asks for instructions while it's learning and while it's doing the task. And we make sure that things like pathological solutions to the problem don't happen. One way to get to Mars really quickly is, to escape from Earth and propel yourself by dropping a bunch of like nuclear explosions back at Earth. That would work. That would get you to Mars. This project called the Orion Project in the 1950s, although plan was to detonate the nuclear weapons when they were like far away from Earth. But this is not a solution we would favor. How do we make sure that AI systems don't do things like that? Cool. So I've only talked about a subset of what the safety team is working on, but we have around 15 members here. Some of these efforts were done in collaboration with DeepMind and various academic institutions. We have a number of kind of interns and faculty affiliates, but we're safety team is continuing to hire, and we're interested in further advancing these in other areas.
Thank you so much, Dario. Hello, everyone. We are now at the conclusion of today's morning talks, but before we break for lunch, I would like to invite all of the volunteers who are joining us today from OpenAI and Berkeley and Nueva School to please come up to the front. So as we proceed into the afternoon hackathon and breakout sessions, these will be the faces that will be around to help you, that you should ask questions to. These people are all talented researchers or contributors or engineers in this space. Many of these people are employees of OpenAI, and we also have, I think the only person here who's not currently employed by OpenAI was previously employed by OpenAI. So if you want to pick our brains about what it's like here, what we do, why it matters, please feel free. Can we just have everyone give maybe a sentence to introduce themselves?
Sure. I'm Daniel. I work on the safety team as an ML engineer working on the language fine-tuning project from Human Feedback.
Yeah, Matthias, I'm on robotics.
I'm Ethan. I'm on the safety team working on model-based RL and safe exploration with Josh.
I'm Carl. I'm on the games team, primarily studying transfer learning and procedurally generated environments.
My name is Dylan. I'm a PhD student at UC Berkeley, and I mainly work on preference learning.
I'm Amanda, and I'm on the policy team here at OpenAI.
I'm Ere. I work on the safety team on safe exploration.
All right. And another thing that I want to say, thank you all so much for being here today. Something that I hope we can do is really make this a useful experience for all of you. And I hope that over the course of the day that you give us feedback about what you find helpful and not helpful, and what it is that you're hoping to get out of this experience, so that we can figure out how to help you get to that. And thank you so much. Please enjoy lunch.